have Rodrigo de Salvo Braz here from UC Berkeley, where he's doing a postdoc with Stuart Russell's team. I'm very excited about this topic area. For quite a few years, the uncertainty in AI community has focused on largely propositional representations, Bayesian networks, and all this various diagnostic reasoning. Predictive modeling typically assumes you have a fixed set of propositions. And one of the directions that's kind of exciting is in opening up our systems to the open, to have more of an open world intelligence, is to mesh first order inferences with the probabilistic calculus, and there's been a kind of explosion of representations. We call it an explosion. I call it a mini firework of representations that combine first order logic with probabilistic inference. Rodrigo did his master's and bachelor's degrees at the Universidad de Sao Paulo, and after that he got fascinated by intelligence and went off to Brown University for a couple of years in the cognitive science department, doing work in neural nets and in descriptive models of various kinds, and as we discussed last night at dinner, got a little frustrated with that work and went off to pursue his PhD more centrally in inferential methodologies, core AI, and this was at the University of Illinois, Champaign-Urbana, working with Ayel Amir and Dan Roth and others there. He's been a postdoc in computer science at UC Berkeley, and just recently informed me that he's probably going to be taking a position at SRI pretty soon to continue this work as an adult, the full-time researcher there. So Rodrigo on first-order probabilistic inference.
Well, thanks for the introduction and for having me over. It's very exciting to be here. I have always wanted to visit Microsoft Research. It's nice to finally make it. So today I'm going to talk about my work in my PhD and also in the postdoc. It's actually two different parts of the same subject. In my PhD, I worked with what we call the lifted first-order probabilistic inference, meaning inference that's performed not only on a first-order representation, but the inference itself is also capped at the first-order level, as opposed to having a first-order representation, generating the propositions, and then doing the inference at the propositional level. So that was my PhD thesis. Then I went on to work with Stuart Russell. He was also working in first-order probabilistic inference, but from quite a different point of view. He was working with a language that was more expressive, more complex. He was working with open universe assumption. But his inference was still propositional. He was working with sampling, whereas I was working with simpler languages and more sophisticated inference because it was first order. But then because of that, I couldn't deal with as much expressivity as he did. I didn't have the open universe assumption. So it was a nice compliment to work with him on that, and that's what I have been working on in the past year in his language that he calls BLOG for Bayesian logic. So I'm going to talk about those two topics, and hopefully one day they will integrate nicely, and we're going to have all these things in one. Yeah, so that's it. So just ask any questions, fireworks if you like, for questions, because sometimes I find that some of this topic may look ambiguous to some people. It's good to clarify things right away. If you want to follow, I'm surprised people don't have laptops here. Usually everybody's like with their laptop. Amazing.
I'll turn it on.
There you go. So for those that have laptops, they can follow the slides from our webpage. All right, so these are the parts of the talk. First, I'm going to talk about first-order probabilistic inference in general, the goal that it represents, what kind of things we want to achieve in the future with that. Then I'm going to talk about my PhD thesis, lifted inference, then dblog, which is an extension to blog that I have been working on, and the conclusions. So the thing I'm mostly interested in is to abstract inference and learning from different AI problems, right? We are all working on different problems in AI, and even though we share so many techniques, so many ideas about inference and about probabilities and so on, still, often it is the case that we have separate solutions that are tailored to our problems. And of course, that makes it harder to reuse those solutions to new problems that come along, and it's also harder to integrate problems. If you're working on a problem, I'm working on another one, to integrate those two solutions, it may be quite a piece of work, and we have to rethink our models because of that. So it would be nice to abstract all these problems and solutions by separating the knowledge and the inference and learning mechanisms that we are using. And once we do that, hopefully we can do this. We can have just one box that does the inference and learning for us, so we can just put in the knowledge about specific problems and use that. That's a vision that AI has had since the beginning of AI, I suppose, but it's still something that's not quite realized. So if we want this magic box that does inference and learning, what should it do for us? One thing that everybody seems to find very useful, especially if you're describing more complex problems, is to have predicates or relations and quantifications over objects. This is something that's very powerful. You can describe many different problems using this. So at first, people did that with logic. But then we also want other things. For example, we'd like to have knowledge that has varying degrees of uncertainty, because often that's the case in problems, that we have knowledge, but that's not a certain knowledge. Here, I'm not committing to any specific uncertainty representation. So I'm just using these brackets, these red brackets around my sentence to say, this is uncertain in some way that I may commit to some form later. But just to say, it may be that I have a tank. Usually that means the color of the tank is green, but not necessarily. So those two things are pretty important in different problems, different domains like language and vision and many others. And eventually, even though that's not something I'm concerning myself with right now, but you also want this box to be able to use other things like modal knowledge and utilities and things like that. But for now, we're concentrating on the predicates and not probabilities right now, uncertainty. So I was talking about integrating problems, right? So if I have domain knowledge about some common sense reasoning task, I'm thinking about a military situation with tanks and planes and the colors of objects and so on. I have that knowledge there. And I also may have, even related to the same domain, something involving natural language processing. And I have also knowledge involving that, about how verbs interact with the meaning, what does it mean to use the verb attack, and so on. And if we share this inference and learning module, then it should make it easier for us to actually integrate those things. And what's the point of integrating that? The point is that you have a lot of synergy, a lot of feedback between those two pieces of inference, of knowledge going on. You can resolve language ambiguities by using common sense reasoning, facts that you are also observing. So bringing everything together may help you with all of the problems at once. You can use the language for the common sense and vice versa. I think that when humans solve problems, they use that a lot, and I think that's a major direction for AI, to integrate things as much as possible. And that's why I'm so interested in, a very general language that can do that. So I was talking about predicates and things like that, and uncertainty. Logic has those objects and properties, a very rich language, but then for standard logics, the statements are usually absolute. So that doesn't do what we're trying here. And graphical models, which are and machine learning techniques, they involve lots of uncertainty, but then usually, as Eric was saying, you assume a fixed set of propositions, and if you have objects that parameterize different propositions, it's not so easy to use that with those models. You usually have to have a separate module that generates new instances of problems for you, and it's a separate, different stage. And usually that's even manual solution, so that's not so convenient. So just to give you a flavor of what you may do with graphical models if you need to use objects and knowledge that is quantified. If you have that piece of knowledge there, so you're saying that an object is either a tank or a plane, and if an object is a tank, usually the color is green and so on. And if an object's next to each other to a tank, then probably it's also a tank. So if you want to use that kind of thing and you have the evidence that the color of a certain object is red, the other is green, you can create a graphical model that represents that. It's important to notice that even though I'm naming these variables with this not so usual notation, parameterizing with parentheses here, from the point of view of a graphical model inference algorithm, those are just strings. They don't know the structure that's involved in this problem. They don't know that this is the same type of variable as that, and that the same type of knowledge applies to both of them. So the algorithm cannot take advantage of that structure. Also, you have to do this transformation, right? And that's not something that the framework of graphical models necessarily brings to you. That's something that you have to come up with a solution for yourself. And as I said, the algorithm doesn't know that this is talking about objects. For the model, for the algorithm, this is just a bunch of random variables. And another interesting thing is that if I have a different evidence, I still have the same model, I still have the same problem, the same solution. I would like to have one model that can be used with different evidence. But here, every time I get new evidence, I get a different graphical model. So formally, technically speaking, I got a new model, a different model that formally is unrelated to the first one. And it would be nice to be able to formally establish how they relate to each other and that they in fact are representing the same knowledge and the same things. So we also lose that kind of thing if we do something like this. So what I just showed you is a technique called propositionalization, which is just generating the random variables from first-order representations. So a lot of people worked on something like that, right? They came up with languages that were very expressive, and when they actually had to do inference, usually they will create a graphical model with the disadvantages that I mentioned before, right? And these languages, they have all different sorts of flavors. Some of them look like graphical models, some of them look like logic, some of them look like databases, some like description logics. Actually, I think the field took quite a while to understand that these things were doing essentially the same thing. It wasn't so clear at first. It wasn't so clear what the semantics of a probabilistic relational model should have. So that's why I think we got so many different models. And eventually people started realizing we're really just talking about predicates, and each ground literal atom is going to be a random variable and so on. So you also have from Hackerman, Meek, and Kohler. From MSR, you have the system DAPR. It's one of the systems in this line. So what people use is what I would call smart propositionalization, because they don't generate all the propositions. They don't just dump a set of propositions and generate a graphical model. They try to do something smarter than that. They only instantiate those variables that are relevant to the evidence and the query at hand. And so you can actually create something that's a lot smaller than you would just by propositionalizing. So that's usually the flavor of what people do. Just to give you an idea about this type of model, one of them, which I find pretty typical, is Bayesian logic programs, which by De Head and Christian Kirsten. So they designed the language to look like Prolog, but instead of using the usual Prolog implication symbol, they used the conditional probability symbol, because these are like Prolog rules, but they actually have associated CPTs and also combination rules in case you have two different rules that are parents to the same variable. You need to somehow combine those two different CPTs into one. So if you are given this bunch of rules like that, then you have something that will generate graphical models for you. So that's more or less how it works. If you have to decide whether a battalion needs rescue in some kind of situation, and that depends on whether there is a soldier in that battalion that's wounded. So if you have a wounded soldier, you need a rescue operation there. And the way it will work is by applying prolog inference and building a proof tree and using that to build a graphical model like that. So by doing that, you actually concentrate on the random variables that are actually relevant to your problem. You don't propositionalize everything. But still, you go and instantiate, in the case of a battalion, you're going to instantiate variables for all the soldiers that you have in that battalion. This generation of graphical model happens even before you actually start doing the probabilistic inference. So say if you determine that a soldier is wounded, that doesn't help you preventing the instantiation of other variables, because you could in principle think of that, right? I already know this guy is wounded, I already know I need rescue, but because we're generating the graphical model before even considering things like that, it's going to generate the graphical model first, and then it's going to do the probabilistic inference. On the other end of the spectrum, something that it's a first-order model that looks like graphical models. It's work done by Lasky called multi-entity Bayesian networks. It's essentially a bunch of templates. Each of them look like a fragment of a Bayesian network, but then the random variables have these parameters. And in this case, the model does know that those are parameterized random variables and uses them to instantiate new fragments. So if you give evidence, you give a certain situation, it uses those objects to plug into these variables here. Then you have a bunch of fragments that have to be combined into a new, to a regular Bayesian network, and then it does the inference. So you just instantiate the fragments and you put everything together. So here you have two fragments of the same variable, you somehow combine. And not surprisingly, you get something very similar to what the Bayesian logic programs do. You get a similar graphical model here, even though the representation looks pretty different. Okay, so that's kind of work people have been doing until pretty recently. In my PhD thesis, I did this lifted inference approach, which I'm going to explain now. Any questions so far? Just to clear that up. All right. So, lifted inference. Suppose that I have that same query. I want to know if a certain battalion needs rescue, right? Instead of instantiating random variables for each of the soldiers, like we were doing before with those other approaches, I could do something that looks more like logic inference, in which I determine the kind of things that will be relevant to my query. But instead of instantiating everything, I leave them instantiated. I just say, well, I just need that kind of that class of random variables to answer this query. I'm showing this is not a formal explanation. I'm just giving the idea about how you can go solving this problem without having to actually instantiate everything. It's the way that maybe most people would think about solving it if they had to do it by hand. We wouldn't start thinking about each individual soldier if we had to decide that kind of thing. We would think, well, a battalion has a bunch of soldiers. I have to check whether the soldier is in the battalion, is wounded. So how do I do that? If I have another rule that a soldier can be wounded depending on whether the battalion has been attacked, then I can decide, I can check if the battalion has been attacked and think about that. Well, the battalion has been attacked, so I have so many soldiers. Each of them has a chance of having been wounded. So what's the probability that I do get at least one wounded soldier? So I think that's how most people would do that by hand. They wouldn't go over instantiating everything. And it's a faster approach. You don't have to instantiate. It's more compact. Maybe it's also more intuitive. And it keeps the structure of the problem, right? Because during inference, I know that This represents a class of random variables, and I know that they are all related to each other, that they all have the same knowledge on them. And I have that information available for my algorithm. I can use that to make better decisions. So that's the gist of lifted inference, just keeping things uninstantiated as much as possible. This is just a very quick review of Bayesian nets. I think you guys are up to date on that. So,
I have a question about
yeah,
previous.
sure.
So you have sort of I don't know what to call it, the any concept. Like if any soldier has been wounded, then that variable is true. And then you mentioned having to do this inference that an attack causes a probability of wounding of one particular soldier, and if you have n soldiers, what's the probability that no soldier is wounded? That's a complicated thing. How many of those sort of complicated atomic things does this have to be able to do?
Why do you say it's complicated? You have an independent probability of each soldier being wounded, right?
Right. In and of itself, it's not complicated. In and of itself, it's that's a procedure that you can follow to see that if you have some probability of something happening to any member of a collection, then what's the probability that it hasn't happened to any at all, or it's happened to one of them? Is there any other type of
I see what you mean.
inference that
You're talking about? This is almost like an inference step,
right.
A way of doing inference. Yeah,
It's
almost like an inference rule.
Right. Are there other inference steps?
Yeah, that's a good point. This is the main one. That's the one that's the essence of it, I would say. But
Each thing in a collection has a probability by itself, and then
but that doesn't work for all situations, right? Because you may have situations in which things are not as independent. And then I'm going to talk about that. There is another way of doing it, which I don't show right now, but takes into account the dependencies between things. So yeah, you can think of it as inference rules, and you may have some of them available. We have two different ones, and we have a third one that kind of links the first two together. It maps one situation well, after I talk about the actual operations, then I'll mention this third one. Okay, so Bayesian networks, you have a joint probability that's a product of conditional probabilities. You can also use factor networks, which is a notation that I use more often, so I'm showing it here. This is essentially the same thing. You have a joint probability that's proportional to the product of these functions. You can represent that Bayesian net using factor networks if you want. Then you have the task of marginalization. You're just summing out a bunch of variables. You can do that with variable elimination. You can efficiently factor functions out and start obtaining new factors. Here I'm using the color green to show new factors obtained by summing others out. So you do that, and you eventually get a function that's only on your variable of interest, and that gives you a marginal probability. So I was just showing that to kind of introduce graphical notation that I was using and so on. So if I have a factor network with lots of redundancy like that, I have, again, here the parentheses only have meaning for us, not for the model. I have several diseases, and I may have epidemics of those diseases going on, and I may have people who are sick with those different diseases, and people may be hospitalized or not. So whether Bob is hospitalized or not depends on the various diseases he may have and so on, and whether people are sick depends on whether there are epidemics and so on. And I'm assuming here, and that's a very naive model, that this function is exactly the same as that, so that if there's an epidemic of flu, the probability of someone getting that disease is exactly the same as if there's an epidemic of measles, someone getting that disease, getting measles, which it's a naive thing, but will do for illustrative purposes now. So if I have a model with lots of redundancy like that, I would rather represent it in a more intuitive way. I'm just talking about different diseases and people getting sick and being hospitalized. So I could just say, well, those are the relations that I have in my model. And I have, this slide just has the point of showing and defining terms. So I could call those classes of random variables atoms just because they are pretty much the same thing that you have in logic. And you have the logical variables, which are the parameters to these atoms. Those factors that actually represent many different instances of the same function, we call par factors for parameterized factors. And we can also constrain their instantiations. I can say, well, that factor holds between instances of those two classes for the cases in which P is different from John. So for John, that doesn't apply. So that's the kind of representation that I'm using for lifted inference.
Because you could, like that potential, you could say.
You mean I could represent that constraint as another factor? Is that what
Right,
I
as
said?
a parameterized factor.
I could do that. We keep them separate because those are deterministic factors. They have their own different behavior, and it's more convenient for computational purpose to keep them as constraints. It's going to be hopefully more clear when I show it. So what's the semantics of such a model, right? So if I give you this first order model, what's the semantics of it? It stands for exactly the same thing as if I propositionalized everything. It stands for its full instantiation. That doesn't mean I'm actually going to do it. It just means that's what it's representing. That's the joint distribution it represents. And each factor here is just going to be the instantiation of the par factor with particular objects. If I do that, I have a standard graphical model and I have a joint distribution. So let's see the operations that we can do with more detail, right? So the first one, which is the one we were talking before, is inversion elimination. And inversion elimination works the following way. In just one step, I can sum one of the classes out, just like that. It's very much like variable elimination, but of course it's not variable elimination because here I'm talking about classes of random variables. I'm talking about when I sum over this, it means I'm treating this atom as if it were an individual random variable, even though it's not. That's how the operation works. And of course, to do such a thing, you have to justify that it's correct, that you can treat an atom as an individual random variable, and that's still valid, right? But that's what it does. So you just sum it out, you get a new function that's on the remaining classes, the remaining atoms, and you have a new first-order representation that represents the marginalization over the instances, all the instances of seq PD. Yeah.
So here, so far you have not shown condition probability tables between any of your standard models which start bothering because you start doing some action. So if I understand that correctly, for a specific P, if I take, I have a probability of epidemic, I have probability of sick given epidemic, and I sum over the sick and I get the probability of epidemic.
Yeah.
And if it's the same for all P's, then of course I can do it for an arbitrary P. Is that what you're assuming? For every person, the relationship between sickness and epidemic is the same.
Yeah.
And therefore you do it once on an instantiation.
Yeah. That's right, but it doesn't work all the time. Because here these variables, they don't interact with each other. The instances of seq PD, they are not interacting directly with each other. If they did, then if you work out the math, you see that you cannot do that. If you do that, it's just going to be incorrect.
Are you pushing to a direction which you look on the highlight on the first-order representation,
Mm-hmm.
and you do something there that is more efficient in some ways than going down to the composition and doing it. Or
Yeah. Actually, the rest of this slide is this, right? So the idea is that I could instantiate everything, do variable elimination over all the instances, obtain these guys here that are just over epidemic random variables, and now these instances can be represented by that. Instead, I'm just doing it directly on the first order level. I never go down on the propositional level. You can think about resolution, right, in logic reasoning. If you have first order resolution, you can look at it from that point of view. You're doing resolution over quantified clauses. And it is just as if you had instantiated all the clauses, done resolution in each of them, and then going back to first order level. So this is the same idea. Yeah.
So I'm still a little confused. So you're still summing over all sick, like all people times disease number of sick predicates, right? The sum that you showed is still a sum overall, like number of people times number of diseases.
No, the sum is just over one symbol. I pretend that's an actual random variable. Let me get that. What I do, so this is a binary variable, right? So I'm just going to say, suppose this is false. I plug it here.
I mean, it's false for all people and all diseases, or for a given person and disease.
You can think of it for any person. I'm going to do a summation for... Because these things are completely separate, right? They are like this, have this parallel structure. I can pretend that I'm doing the summation just for this guy. Once I do it for this guy, this is going to be exactly the same because the potential doesn't actually depend on the objects. It only depends on whether this is true or false. So if I do the summation for here, I obtain a new function that depends on that, and that's going to be exactly the same function I'm going to get for this one. Because all these sub-problems, they all have exactly the same structure. And the actual numbers don't depend at all on the objects.
So the number depends on the true or falseness of the predicate.
Yeah.
So the sum needs to know, I mean, you're going to end up with true terms and false terms. So, I mean, do you just need to know the number of true and number of false, and that's how you do the sum? I mean, you can move on if you want.
No, that's okay. You're asking if I need to know the number of objects that are true and the numbers that are false?
It's going to depend on that, right? So,
Yes, but because you have this nice structure here, and it's not something that's general, it's only some situation like this one, you can actually ignore that fact. Because they're all independent, so you can, it's as if you're factoring things out. Suppose that you do decide to do it on the propositional level. You're going to have your summation, it's going to be a summation over all these random variables, right? All of them. You're going to have many of them. And you also instantiate all the factors. Because they're all independent, you can factor each instance of a factor to its corresponding summation. And you're going to end up with a summation over one factor here times a summation over another factor here. And they're all going to have exactly the same structure because they don't depend on the object. So you do the first one or whatever, and you know the result for all of them. And then you get these guys, a bunch of instances of factors that all look the same. And because they all look the same, you can just abstract back like that. I'm going to move on because otherwise it's going to take a lot of time. But we can talk more about it if you want. Are you on my schedule, by the way? Okay, good. So inversion elimination. This is actually something that was proposed by David Poole in 2003. And he didn't actually formalize it very completely. And the way he presented it was as if it would work every time. Basically, he was saying what you were saying more or less. That, oh, I'm just using generic objects. It applies to all the objects. But actually, that doesn't work all the time because if the random variables interact, then you don't have that nice separation anymore. So what we did in the first paper on this subject was formalize it more carefully, and then we realized, okay, that doesn't work all the time. What are the situations that it is correct, and what are the ones that it's not correct? So here's the limitation, right? So because I have all these separate structures that have exactly the same structure, I can do an operation on one of them and I'm going to get exactly the same result. So it works. But if I have something like this, right? Suppose I say, well, what's the relation between the variables for epidemics of two different diseases depending on the month? So I have that factor, right? That relationship. I cannot just go, suppose I want to marginalize over epidemic. I cannot just apply inverse elimination and obtain something like that and I'm done. That's not going to work. I'm going to get something, but it's just not going to be the correct thing. And the reason for that is that if you ground something like that, you obtain this. You obtain a very connected graphical model. And things are not separate anymore. So when you're summing over one of the variables, that's going to influence the summation of the other one. So it's not true anymore that the summation of over one variable is going to give you exactly what the other would give. So that's the limitation here, inverse elimination. And because of this limitation, we started thinking of other ways of solving things. So for this problem, even though I have all this interaction between these random variables, this is still a very simple thing in a way, because these are all symmetric variables. They all have the same structure, they all have the same knowledge on them. So it seems unnecessary to treat each of them individually, because it's really just a mass of symmetric variables. So can we take advantage of that symmetry? So as we were talking about before, we need to consider joint assignments of that. And that's going to be an exponential number of them. But because they are symmetric variables, an assignment, when I say, well, this is true, this is false, and so on, it doesn't really matter which ones are true, which ones are false. It only matters how many are true, how many are false. So if instead of iterating over all assignments, I just iterate over the histograms, the number of truths and false that I have in that cluster of variables, that's going to be enough. And that's going to be a polynomial number of assignments instead of an exponential one. So that's the other operation that we were talking about, two different operations, and that's another one, counting elimination. And that's a more expensive operation, because even though you have this polynomial number of assignments, it's a number of assignments that does depend on the number of objects that you have. I didn't mention that before, but inversion elimination actually doesn't depend at all on the number of objects. You may have 1 million objects, doesn't matter, because you're going to do the summation for this generic object, and you're going to do it only once.
Basic network or one specific, is months makes the two epidemic independent, or not? Is it a chain, or they're all related?
Well, this is an undirected graphical model, right? So
undirected, where it's a click between the three?
Yeah. So this notation that I'm using is just like a Markov network, only I'm actually explicitly representing the functions over the... So this is one click. Well, I'm not linking this guy here, but this guy is linking to each of those functions, right? This is a proposition. So it links to all of those instances. Yeah, now I'm kind of regretting not having put the equations here. I think you guys would have appreciated that more. But I can go over that with you if you like. I just wanted to keep it more high level, not get down the details. But the idea is that you're going to have a summation again, but instead of being a summation over generic random variable, you're going to have a summation over the number of values that you have in this cluster. And then you're going to get a potential just on the remaining variable, month. So basically for each month it's going to have a different potential. Yeah?
So this is assuming you don't have any evidence that distinguish between like flu or measles or rubella. So what if you have evidence?
Yeah, that's a good question. That's actually a crucial point, because this all depends so much on things being indistinguishable and symmetric. And if you have knowledge about specific objects, then you actually have to to separate those cases. And you do that in the following way. If I tell you, I know for a fact that there is an epidemic of the flu going on. So what you do, you come here, and that's why I was keeping the constraints separate, because they come really handy when that happens. Because then I'm going to break this par factor into different parts. A par factor is just a set of instantiations, right? I'm going to separate the instantiations involving the flu and the instantiations that don't involve the flu. And the ones that don't involve the flu, it's what we call the residual. It's going to be like this. The one different from the two, but also different from the flu. And the other is going to already be instantiated. One of them is going to have the flu. So you separate that. And then once you do that, then again, every par factor involves things that are completely undistinguishable and symmetric. So you go on with your calculations. But in the presence of evidence, you have to do this. It's what we call shattering. Actually, it's even more than, it doesn't even depend only on evidence. If your knowledge distinguishes things in some way, if I have some special rule for the flu, then I have to do that as well. I have to combine that with this rule and separate them. Actually, this is an interesting thing because, in terms of logic, because it starts looking a lot like resolution and unification, because when you have to identify the intersection between two par factors, it looks very much just like a unification and breaking clauses like we do in logic. So it's an interesting link to think about logic inference and this type of inference. It starts looking like that. And actually, that's a major limitation of the approach right now, because if you have a database, right, with facts about each of your objects, then this is not going to be helpful to you at all, because you're going to have to look at that database and take all those facts into account and basically propositionalize. You're going to have things for each object. So it wouldn't be helpful in that case. So that's still a major limitation. It's not a limitation that's that you cannot get around it, because you can do something like, I'm going to talk about that later, but essentially you can do some kind of approximate inference that when objects are still not the same, but they have similar properties in similar situations, then you can still consider them as part of the same class. So there is a generalization that takes this approximation into account. But right now, because this is exact inference, we're not doing that. Any other questions before I move on? So this is lifted inference. If you run experiments on this, very predictably you get graphs like that, right? These operations don't depend, the first one, inversion elimination, doesn't depend on the domain size at all. So if you propositionalize and you do inference, it's going to be an exponential curve, and the lifted inference remains the same. And here, even though the count elimination does depend on the domain size, it's really hard to get a graph that shows that, because the propositionalization of it still grows a lot faster. So for this case in which you have clusters of symmetric variables, those are much faster operations than propositionalizing. All right, so I'm going to move on to the second part of the talk, which is about blog and deblog. So have 15 minutes, right? So it's not much. Long, all right. So let me tell you a little bit about blog, Bayesian logic, which is the work that Brian Milch and Stuart Russell have worked on during Brian's PhD thesis. So it's a probabilistic logic language, just like those others I presented. And its inference is just propositional sampling. You propositionalize variables as you go and you sample them. And what distinguishes blog from other approaches is those two things. It's an open universe language, so it doesn't assume you know the number of objects in the world. You have distributions on the number of objects in the world, which is it's a nice feature and very realistic, because usually we don't know how many objects are out there. And it's also a very expressive language. It looks very much like a programming language. You can write very arbitrary things in it. So here's an example of a blog program. So you declare types. So I say I have this type battalion, and the number of battalions is a uniform distribution. I have this property of battalions. That's a Boolean property. That's just going to be a Bernoulli distribution there, whether a battalion is large or not. You can have the region of a battalion. It's going to be a natural number, and that's a distribution over from 0 to 3. And then you have another type of object, soldiers. And the number of soldiers, it's a parameterized variable. It depends on the battalion. So for each battalion, you're going to have a different set of soldiers. That's going to be it's going to have a distribution too. And you can write that the number of soldiers of a battalion is going to depend on whether the battalion is large and the region of the battalion. And then you can place queries like what's the average number of soldiers per battalion, for example. So because I have distributions on the number of objects, that's an open universe assumption, and also it's a pretty expressive language. I didn't really show, when I was talking about part factors, I didn't want to be going down to details of syntax and so on, but usually those part factors, they are just tables, right? So it's a much simpler representation as opposed to here, in which you actually describe the computation of the distribution much more carefully, and you have a lot of structure available there. So it's a more expressive language. You're also talking about sets of objects. You're talking a variable that, average, that's going to be over a set of objects. It's a much more expressive language. So, inferencing blocks. So just going back to that first example that I was using of a soldier being wounded and a battalion needing rescue and stuff like that. So I'm just writing that in block now. The only difference is that the probability of a soldier being wounded, I'm making the model more detailed now, and I'm saying that it depends on whether the soldier is experienced or not. There's the probability of them being wounded is different. But basically, that's the same example as before. So if I have a blog like that, a blog model like that, and I want to know what is the probability that a battalion needs rescue. So how does the inference work? It's sampling, right? So when I have this query, I need to know what its distribution. So that's going to depend on its parents. And its parents, as we see here, you have this, it's an existentially quantified sentence. So that's going to depend on all the soldiers. I have to look at all the soldiers, the set of soldiers, and see which ones are in the battalion and how many of them are wounded. So that's one of the parents of my variable here, is the set of soldiers for that battalion. So I sample values for that. And once I have a set of soldiers, I have the parents of this variable that I need, which is going to be the variables wounded for each of the soldiers. Once I do that, I have to sample, okay, is the soldier wounded? Now I need to sample a value for that. I need to determine its distribution. I need to know which, I have to have values for its parents. So the parent there is whether the battalion has been attacked. So if I do that, I can sample a value. If I get false, it means the battalion is not attacked, so the soldier is not wounded. And unfortunately, I'm going to do the same thing for all the variables, right? Even though I know that the battalion is already attacked, I should be able to tell that all the soldiers are not wounded because the battalion is not attacked. But I'm going to sample values for each of them, and it's going to be false for all of them because that's the distribution. And because of that, whether the battalion needs rescue or not is false. So that's how it works. Just another example. Yeah.
The notion that the battalion has members, i.e. the soldiers, and then if this attacked thing holds for the battalion, it holds for each of the members.
Mm-hmm.
Right? You needed to know that attacked, it wasn't an individual soldier that was attacked, but that the battalion was attacked, and therefore each of its members was attacked.
I think when you write this statement there, let's see. So here, right? If a battalion. So I have this variable that says to which battalion a soldier belongs to. That's something I didn't go through over in very much detail, but when I have a number statement for soldiers, I'm saying for each battalion I have a number of soldiers, and that actually constitutes a function on soldiers. So I have this function called battalion of, that's going to give me the battalion to which the soldier belongs. So if I do that, I have, if the battalion to which the soldier belongs is attacked, then I have a, right? Does that make sense? I don't know if that answers your question.
Yeah, so if you go back to that picture,
Yeah.
the way you were explaining it, you were sort of going through variable by variable and saying, okay, what parents do I need to know about in order to figure out if this variable is true? And you got to wounded soldier 1 and you said, oh, I need to know about attacked. And then when you got to the next wounded soldier, you knew that that was going to depend on that same
variable. Yeah.
Presumably in other cases it would depend on a variable that's not the same.
Yes.
So there was this membership concept. Are there any other concepts that we should know about that come in handy when you're deciding what depends on what?
Well, I don't see those are separate cases, because what I do is always the same thing. I look at the statement, the dependency statement for this, and it's saying, well, look at the battalion of this soldier, and that's going to be your parent. So it determines that, okay, I need to know this variable. This guy is going to do the same thing, and it's going to, just because that's how that computation works, it's going to get exactly the same variable, then it's going to look up there.
So the language allows for these functions like battalion of, which are sort of arbitrary, and you can define
Yeah.
them as you wish, and then you're just sort of changing
Well, they're not arbitrary exactly because
how expressed they get.
this function battalion of is what we call an origin function. It's actually, it has a very, it's not even a probabilistic variable, because when I need to know the number of soldiers in a battalion, right, I have to sample that. Okay, I need to know how many soldiers this particular battalion has. I sample a number. In that case, it was 73. When I do that, I generate 73 objects that I place on my universe. And then I define the origin function for each of them to be that battalion that generated them. And that's a fixed value for all of them. So when I go to wounded dependency model, I say, well, is the soldier wounded? Then I plug the soldier here, then battalion of is already determined because that was determined when the soldiers were generated. So I have a value here, battalion 13. So now I know that I need to know whether battalion 13 has been attacked or not. And then I sample that.
So you have this sort of generation story, right? Like the
Yeah.
battalion sort of has all these soldiers.
Yeah, it's a very much generative model.
How would, like, for instance, would you be able to model like a set of battalions with a set of soldiers where different like a single soldier can belong to battalions, like, you know, can be generated from 2 places, or like, you know, or does that get to like beyond
No, you can do that. You can do that, but those wouldn't be origin functions, because the origin function is defined as a parameter of the number here, right? Once you have that, you're saying all the soldiers are coming from the same battalion, so that's it. But you know, you can define arbitrary functions on things. I could also have another variable here, say alternative battalion of, and then it could be anything. Yeah, and then I could use that variable if the battalion has been attacked or the alternative battalion has been attacked. So even though those origin functions, they are under the hood different, they are treated, you can use them in the same way as any other function. So it becomes a very uniform process. So do you see now that it's actually always the same case, that you're always looking at the parents like that? I'm asking like the other.
Sort of. I mean, I guess what I'm getting at is like this is like a programming language. And if
Yeah.
you define a programming language, you know, you say, okay, I have base types, I have integer, I have characters, I have
Right.
real numbers, I have basic atomic functions, I can add, I can subtract, I can multiply. And I'm trying to get at that's what exactly is this set of basic operations that you can define here, and basic
Yeah.
types of types and so forth. Like if you do define it as a programming language,
Yeah, you have
what's the set of things?
You have the built-in types like natural numbers and Boolean and things like that. You also have user-defined types like soldier and battalion. And then you have these operations, right? Here I'm not showing many of them, but you have things like plus and minus and all that. And it always works the same way. You execute these instructions here. Every time you need the value of a variable, you look to see if it's already defined and already has a value. Or if it's not, then you sample a new value for it. And when you sample a new value for it, you're going to trigger this recursive process in which you sample that variable's parents and so on. So eventually you sample them, and then you have this partial world representation. So it's always just this loop. Sample parents, get distribution, sample value for variable. And if you get evidence, that's the same thing too. You get the evidence and you need to know to sample parents of the evidence and see if that's a likely explanation and so on. So this is one example, right, in which I had to sample values for all of the wounded variables. I can have another one. Suppose that the battalion has been attacked now, that I'm sample things, and in this particular sampling run, the battalion has been attacked. And now it's a different sampling run, so I actually have a different number of soldiers. In this other world here that I'm generating now, that battalion has 49 soldiers. So the battalion has been attacked. So now, and that's an interesting thing in blog, right? It uses this context-dependent independence here, which is context-specific independence, which is now that I know that the battalion is attacked, now this variable matters. To know the distribution of wounded, I actually need to know whether the soldier is experienced or not. So if I go through the dependence model here, okay, it's been attacked. So now what's the experience of the soldier? And then I'm going to sample something here. Once I do that, then I have a distribution for wounded. Suppose it's true. And if it's true, actually you have, just like in regular programming languages, right? If you have a disjunction and you get a true, then you know that the result is true. You don't even need to look at the other one. So in this particular case, we take advantage of that, and the other soldiers, you don't actually have to do any sampling because you already answered your query. So. But you have to run this many times, and many times it's going to be that you have to sample all the soldiers. So blog has this lazy evaluation property, which is nice because as opposed to some other methods, right, in which you propositionalize first and then you start doing the inference, blog is doing the inference and propositionalizing as it goes. And as a result of that, it saves work sometimes. So the blog is just dynamic blog, just like you have dynamic Bayesian networks. So it's trying to use blog for temporal models. Now, because blog is so expressive already, you don't really need more expressivity to express temporal models. You can just use natural numbers as time steps, and you just write your statements that depend on the previous time step, and you're done. So that's a legitimate question. Why do you even need to bother about dynamic blog? You could just write a blog model that has time. And the reason for that is that temporal problems have a lot of structure that you want to take advantage of. So you have this Markov property there. If the algorithm knows that that's happening, you can take advantage of that. Also, usually in these problems, you get the evidence and query successively 4 time steps. So usually you know that once you are in a new time step, you're never going to get evidence about previous time steps. And you may want to take advantage of that. So the language remains the same, but it's still nice to use a different algorithm that takes advantage and is more efficient for temporal models. So we are working on dynamic blog. We do make this change to the language that if you just use natural numbers, the algorithm doesn't know whether that natural number is actually representing time or not, right? Because it could be just some natural number. So what we do have this new type, it's time step, which is just natural numbers, but it's actually telling you this is representing temporal structure. So the algorithm knows. But it works exactly in the same way. You just have different literals. Now instead of 0, you have @0, things like that. But it works exactly the same, so much so that if you give this to the blog inference algorithm, it still deals with that, because time step it's just one of the built-in types. But it's not going to take advantage of the structure. So we have de-Blog particle filtering, right? So particle filtering, as most of you know, it just works by, you have some samples for state for a particular time step, and then you get new evidence, use likelihood weighting, and you see how likely an explanation each of them is. Then you resample to get population that represents more likely hypothesis. And we do the same thing in de-Blog. So you have a world there, you have this partially instantiated Bayesian network for a specific, that represents a particular explanation that you sampled. And then, oh wait a second, this slide is still about dynamic Bayesian network, so that's not about blog. But it's essentially the same thing. You just sample the new variables using the time slice and you generate a new particle. So for de-Blog, you have this particles. The particles now represent what I was showing before, that network of variables that require the instantiation of each other and so on to generate an explanation for your query or your evidence. So when you get new evidence, and the evidence is going to be blog statements like that, then you need to explain it. So here what I'm saying is that, well, I didn't actually explain this model, so let me go back really quick. This is about aircraft. I have a bunch of aircrafts. They have their positions at each time step. That's going to be a random walk depending on the previous position. And I have blips that this aircraft generating aircraft in a radar. It can be one blip, or maybe it's not detected in that particular time step, right? The number of blips is going to depend on the aircraft and on the time step. So each time step, I may or may not generate a blip from an aircraft. I can also have another set of blips that are just false alarms. I can have some noise blips. And those blips are going to have the apparent position of an aircraft. That's going to be a Gaussian noise around the position of its source. So here, source is another one of those origin functions, right? That's going to be the aircraft that generated the blip. So I just look it up here. What's the position of my source? Well, actually, that shouldn't be previous time step. Should be the current time step. What's the position of my source at this time step? And then there's a Gaussian noise, and that's the position of the blip. So that's the model I'm using here. So if I have the situation, I'm saying, I'm observing now that the number of, that I have one blip only that comes from this aircraft, that I have exactly one. So it has been generated. And the apparent position of this blip is 3.2. So I need to get a distribution for this variable, apparent position of blip B1 at time 2. Because, yeah, I was using time step 2. So I do that by sampling a value for B1, which in the case here, that's not a very interesting example, because B1 is always going to be the blip. There's only one blip generated anyway. It's not a set of blips per aircraft. So that's going to be a very simple thing. Always, I'm just going to instantiate B1 with the blip that the aircraft generates. And if the aircraft doesn't generate a blip in that time step, it means this particle will have weight 0. Then once I know that, I need to know also what's the position of the source. So I sample now the position of aircraft 1, and that's going to depend on the position of the previous time step. So I use the previous particle as a set of already instantiated variables. And then I explain my evidence, and then I have a weight to evaluate this particle that I just generated. And like before, I have this lazy instantiation. I just instantiate the things that I really need in order to explain my evidence. So now we have an issue that doesn't arise in dynamic Bayesian networks. Because you could think, well, dynamic blog is just like dynamic Bayesian networks. There's nothing new. But you start having some issues that you don't have before. This lazy instantiation is one of them. So just like in that particular case, but now for time step 9. If I get a new blip, and this time it comes from aircraft 2. And suppose that I haven't observed aircraft 2 since the beginning. It's the first blip that comes out of aircraft 2. I'm going to have to sample the position of aircraft 2 at time step 9. But because I have lazy evaluation, instantiation, I'm not going to have any values for that in the previous time step or the previous. I'm going to have to go all the way to the beginning. So the cost of this lazy instantiation of variables is that you may have to do something like that. And so the nice property of dynamic Bayesian nets, where you have a constant update time, would go away in this case.
Are you guaranteed that somehow that doesn't affect the particle filtering that it shouldn't? That you would get the same answer if you would just instantiated those right from the beginning?
Yeah, you're wondering that what I did before didn't depend on position of aircraft 2, right? It doesn't, because the fact that it has not been sampled means it was irrelevant to the evidence. So even if I had instantiated it, the evidence would have exactly the same weight. So yes, it is guaranteed that it doesn't matter. It only matters in terms of cost.
In a real-world system that at scale, we can imagine an adversarial attack on the system to really bring it down by hiding, obfuscating future aircraft and then revealing them in certain ways that would sort of become intractable.
Right. So you could think of something like that. And you know, it sounds like this is a problem.
So if it doesn't affect the probability of the previous time step, why do you need to adjust extension?
Well, because now you got evidence that depends on it. Like up to now, you never had to bother about it. No matter where you were, the evidence would have the same weight. But now, because I'm saying that this blip comes from aircraft 2, and I'm telling the position is here, I need to...
So, I mean, you can instantiate for this time step.
Yeah.
And you don't need to go back.
But to instantiate this, to sample a value for that, I need to get its distribution. And its distribution depends on the previous time step. And it's a recursive thing.
Post-form solution, right? At least if it's a random walk, right? You know it's been
Exactly.
200 steps. You don't have to actually do it.
Right. So, and actually, you know, this is a very common problem in AI, data association. People have worked on that, not with blog, but, you know, just handmade systems. And they have circumvented this problem. They don't generate things all the way to the back, basically using things like closed form. And that's an option that's available to us as well, because we know that this is a random walk. We could also code the model in such a way that's bringing that closed form there. Just like previous work, people had to sit down and think, hey, what's the closed form of this? And then they worked it out in their system. We can do the same thing here. But it's something that's not done automatically. You have to think about it and write it down. This actually... I don't know as much about dynamic Bayesian networks, but I would assume that people may have worked with lazy instantiation dynamic Bayesian nets too, right? And then they would run in the same problem as well. Do you know of anything like that? Because that's not a blog-specific thing. If you have a dynamic Bayesian networks with lots of variables, and many of them are not relevant, and you don't want to instantiate all of them, then again, it would run into the same problem. Yeah.
To do that sampling, so if position A2 at time 2 depends on any of the state for the particle at time 2, then would that mean that you wouldn't be able to just closed form figure out what it would be at time 9? You would actually have to go through the sampling, or can you?
No, I could look at the particular distribution there, the transition distribution, and maybe I could figure out some closed form. Right. Is that what you're talking about?
Yeah, I guess I'm wondering if the position only depends on the start state and then how much time it's been, then you can definitely do the closed form. But if it depends on, for each particle, some of the other state factors that had been sampled in that particle, then it seems like you can't do a closed form. You'd actually have to keep the history of the particle so that you can go back in time.
Because maybe the history of the particle affects
Like if position of A1 affects position of A2,
Yeah, right.
then you need to know A1 at time 2.
Yeah, so the closed form approach depends also on whether these objects are interacting among themselves. Yeah, so
It would depend on the evidence. So if evidence change, so at least your closed form has to take the evidence as input.
well,
The evidence
Yeah,
for
sure.
the previous timestamp.
so what do you do and what people have done in data association models in the past? When you get an observation of something that you don't believe has been observed before, then you use the closed form. Because I never got evidence about this guy, so I know that's the distribution of this time step, given that I got no evidence so far. Now, if you have observed it before, then you have to use the history, right? Because you actually know something about that object. So you may have another closed form, but that somehow depends on the history. So yeah, so you have to do that.
Right now, you're assuming that you deterministically know which aircraft is giving you which bleed. And if you sort of put
Right, that's
uncertainty
not
over
the
there, it's
usual
more
situation.
complex.
Hmm?
So if you put an uncertainty over there,
Yeah,
then you also have to infer about whether the bleed came from aircraft 1 or 2.
yeah,
In that case, closed form won't do anything.
yeah. You're absolutely right. When you don't have, if I just tell you, hey, that's my set of blips, that's their positions, I don't know where they're coming from, then you have to generate the positions of our aircraft to be able to explain that set of blips. And then this problem of retro-instantiation wouldn't occur because you're always instantiating everything. So you always have everything available.
If I'm only getting one bleep at a time.
Even that, right? Because
Okay.
I say, well, okay, where's this blip coming from? I have to instantiate all aircraft and see what's more likely that which aircraft is more likely to have generated it. So then that problem would arise, which is not necessarily a good thing because you would be instantiating everything. And again, you could have a form of lifted inference, right, in which you keep closed form representation for a generic object representing all objects that have not been observed so far. Because those are indistinguishable. You know exactly the same thing about them. You know the prior at the beginning, and you know that you never knew anything else. So you could use some kind of listed inference. And actually, when you look back, previous work in data association, essentially that's what people are doing. They are implicitly representing the unobserved objects with a closed form thing without representing individuals. So, but that's all done by hand, and it's done for specific models. The challenge here is actually having an algorithm that can take a model and figure all this stuff out. Closed forms and lifted inference and all that. So it's a...
So I wonder how this interact with the open universe assumption. So suppose if you at the beginning you only generate a number of how many aircraft you have. Suppose you sample to be 1, and later on you actually have evidence of 100 aircraft. So how do you reconcile?
Yeah, so that's a good point. This is a atemporal. The number of aircraft here is an atemporal variable, right? That once you sample it, it's done, it's fixed. And that's a problem that arises in DBNs as well, because if you have DBNs with atemporal variables, you have to do something smarter than just sampling it once. And people have come up with solutions for that. One of the solutions is to, at every time step, to apply a transition kernel that preserves the posterior, and that changes also the variables of the atemporal variables. We could do that here as well. We could change the number of aircraft at some point, but then you're going to have to regenerate the history. It's going to be a very expensive.
So how do you handle that?
We don't handle that right now, actually. That's still something to be dealt with. We are working on having a MCMC transition kernel that we can apply to blog models, which is not that simple. Once we do that, then we can apply to atemporal models, but then we still have to figure if it's going to be how efficient it's going to be to change those variable values. It's still not very clear to us.
Is there no hope for dynamic programming approaches? Is that just not applicable?
I'm not sure, because the structure here is so, dynamic programming usually depends a lot on, exactly your variables and everything is fixed, But we haven't thought that much about that, so maybe there is hope. So some of the things that we can mention about retroinstantiation is that one possible way of dealing with it is pre-instantiating things that you know will eventually become necessary, even if they're not necessary for the current evidence. If you know the type of queries and evidence that you're getting, a template kind of queries and evidence, then you can infer what variables need to be instantiated. You could even do smarter things like what's the probability of needing this variable and instantiating it according to that probability. So you can do pretty sophisticated things here. Another thing is using things like mixing time to decide how much to sample back. Maybe the initial position is completely irrelevant at this point anyway. So you can also try to make a decision how much to sample back. And the closed form things and the other things that you mentioned are also ways of dealing with it. Okay, last issue on blog inference that's not related to retroinstantiation or even to dblog. Dblog, turns out that as we worked with dblog, we found many limitations in blog. Because this data association, for example, was one thing that brought many challenging things that we had to rethink about blog. So this is one of those items. So just showing here how basic things work, right? Rejection sampling. You get the evidence, then you sample the value for that evidence, and you see if it's equal or not, and then you keep the sample if you get the evidence. Then you have likelihood weighting. You have the evidence, you sample values to know its distribution, and you weight the sample according to the likelihood. Now, suppose you get evidence like that. I'm telling you the set of values for happy P for each person P is true, false. So how do I do likelihood weighting here? I could sample the values of those variables, right? Suppose I know I have 3 people, and then I sample that, and I get true, false, false, and that doesn't match the evidence, so I throw the sample away and I keep doing it. In this particular example, it doesn't look so bad because it's only 8 possible values, but it's still pretty bad. Now, if you have variables with lots of values, then it's going to be pretty hopeless. And if you have continuous variables, then it's really hopeless, right? You're always going to get probability 0 if you just sample the values and then you compare with the evidence. This becomes just like rejection sampling. It's no better than rejection sampling because you're just sampling the values and comparing to the evidence. Even though, technically speaking, this is likelihood weighting. It's not rejection sampling because the evidence is this variable here, and we are not sampling that. But because you have a deterministic function between the evidence and its parents, ends up being just as bad as rejection sampling. So this is one of the problems that we came up. This is very much like, this is the bleep situation, right? If I tell you that's the type of query that's going to be more common in the real application. I just tell you, okay, I'm seeing 3 bleeps and those are the positions of the bleeps. I don't know where they're coming from and so on. So you have to give the likelihood of such evidence. And if you just sample those variables, it's not going to work. And this was not supposed to be here. So here what we do is the following. Instead of just doing blindly likelihood weighting, in which you sample values for the parents and you compute the likelihood, here what do we do? When we sample the value for the parents, we determine its likelihood, and we know here its distribution. We know it's a Gaussian. So now I know that to have a valid sample, I need to have one of those values. So I just do an importance proposal that's going to pick one of those values proportionally to the likelihood of each of them. So if I do that, here I pick, for example, 1.2 for that parent. And then the probability of picking 1.2 is going to be proportional to the likelihood of each value. So I know the probability of getting that value in my specific proposal. I can keep track of that. And then I do the same thing for the second parent. Now I only have two values available. I have this choice. I keep track of that choice likelihood, probability. And then the last one, I don't even have a choice. So now I have a proposal distribution that's going to be much more efficient. It's going to work. And not only that, it's going to pick values not only that are valid, but also that are usually more likely. Because I'm going to consider the distribution of the parent before I pick the value. So this is one of the changes that we did. This is not even dblog. This is just blog. This is just the blog mechanism for giving likelihood to evidence. And the nice thing about that, the important sampling part of it, it's very well known. It's something that people do on a regular basis, but usually people do this by hand. And the nice thing about having this language that has high-level constructs like sets and so on is that the model automatically can look at these constructs and build a proposal that's going to be effective without you having to say anything. This is something, I don't have to write a proposer to get this done. I just write my evidence and the algorithm looks at it and sees that this is a set and that's how I have to do it. So that's one of the advantages of having this higher level structure available to the algorithm. All right, future directions and all that. One of the things I mentioned to you before is that lifted inference is an exact procedure that requires clusters of random variables to be symmetric, and that's not a very realistic assumption. So really we have to do something that uses approximations. The intuitive example here is the following. If I'm thinking about the population of the United States and I'm trying to make decisions, estimate probabilities like in the elections and things like that, I don't have to consider every individual. Even though each individual, I may have particular facts about each of them. I may have databases talking about all these people, but I still can do some kind of lifted inference if I'm willing to ignore irrelevant factors or things that are somewhat relevant but not much, or that's not going to affect the result all that much, so I can ignore that and have something that has a margin of accuracy. So there is a generalization to lifted inference that takes that into account, that doesn't require symmetric objects. So that's a very important direction. Another thing is parameterized queries, right? What I showed before, the queries always were propositions. And the reason for that is that if you have unbound variables in the queries, then you have to keep track of possible values for the logical variables in the queries, and it complicates things. But it would be really interesting to be able to ask something, what's the probability of X being sick of measles? And then the answer is something like this. If X is John, then the probability is such. If X is Mary, the probability is such. If X is someone else, any of the other people, the probability is such. Also, it would be a nice link to logic programming, because that's what logic programming does, right? It instantiates, it binds all those logical variables for you when you give a query. So that's something that's still to be done. Also, we don't have function symbols explicitly, so that's also nice if we could write things like that. As I was saying before, right, the lifted inference language is not very expressive like blog is. So these are all directions to make it more expressive. Also using equality, adapting paramodulation, things like that. And of course, learning the parameters of functions. And okay, the take-home messages here are the following. So it's useful to keep the first-order representation not only for representing your model, but also during inference and using that in the inference. If you do lifted inference, then you have something that's equivalent. It gives you exactly the same answer as the grounded inference, but it's much faster. Oops. And as for deblog, this is about bringing this techniques, temporal processing, to this first-order representations and all the variations that requires. So basically, what I want to do in the future is, to increase the lifted inference part of it and come up with something that's an inference engine that people can actually start using for real problems, and not very different from what Pedro Dominguez is doing with Markov logic networks. He has already a pretty advanced engine, and that's the direction that I also want to follow. Although he's using very different techniques now. So now he started using lifted inference, but before he was also doing propositionalization and so on. And that's it. Thank you very much for your attention, for staying for so much long.
We had questions during Okay, it's our honor today to have Doug Lynette visit us. Doug was in town for the Vanguard meetings, and we thought we'd have him here to update us on his 22-year project. Doug is one of the most passionate people I know in the AI community in terms of pursuing the prospect of endowing machines with common sense, one of the hardest problems we know in artificial intelligence. Doug did his PhD work at Stanford, and in that work, which was quite compelling, he showed examples of systems that might one day become commonplace, that could think about mathematical conjectures and go out and prove them, and even have inside their representations and reasoning notions of interestingness. But I always thought it was a fascinating pursuit. I often define people by what they think is interesting. Doug is now skipping ahead many years, is now the CEO, and I would say CTO probably, and many other positions at PsyCorp, a corporation that had some foundations in the MCC early work on psych, and will tell us about where we stand on combining manually edited as well as machine learned knowledge bases that can perform common sense reasoning.
Thank you, Eric. I appreciate it. Okay, good. So I wanted to talk to you about the relationship between computers and common sense, which, as the title indicates, is historically and pretty much still today a kind of adversarial relationship, much more than it should be. And when we talk about common sense, when we talk about psych, we're talking about the millions of things that you know about the world that you pretty much assume that everybody sitting next to you would know about the world. Things which, if they didn't know, you'd think that they were sort of either joking or insane or something like that. Things like, hearts are usually on the inside of the body, and if you have feathers, feathers are on the outside of the body. And so, if you see a picture of a bird, there's a good chance that unless the bird's in bad shape, you're going to see the feathers and you're not going to see the heart of the bird, and things like that. And causes precede effects, and all the specializations of these things. So, for example, parents are generally older than their children is a special case of causes preceding effects, and so on. Most people in modern Western cultures smile when they become happy. So again, a lot of the knowledge is going to end up being culture-specific or temporally contextualized, and so on. We're not talking about things which are absolutely monotonically, monolithically true over all times and space and context. So there are millions of these pieces of information, and we've represented them in a form that computers can actually do something with other than just remember them and store them and parrot them back to human beings. And kicking and screaming, we've basically been forced to develop a more and more formal, more and more predicate calculus-like representation over the years, over the decades for that. When I say that the knowledge is almost completely language independent, what I mean is that while the system knows things like penitentiaries are much larger than writing pens, that knowledge has to do with the concepts of penitentiary and writing pen, not with the fact that in English you might happen to use the English word pen to refer to both of those meanings. So yes, it's good to have a lexicon and to know what the denotations of words are, but the actual underlying knowledge is independent of language. And yes, we have an inference engine to do automated reasoning. And yes, we have interfaces to communicate with other programs and so on. But by and large, the most valuable part of what we've done over the last 22 years is working out the ontology of hundreds of thousands of terms, and sitting on top of that skeleton, the flesh, the millions of axioms that define and constrain and interrelate those hundreds of thousands of general terms. I talked in my abstract about the semantic web, and in a way, the history of the semantic web is the history of a series of false peaks. People being optimistic that if only they could agree on X, surely computers could interchange their information and arbitrary machine intelligence would ensue. And way, way, way back, that was sort of at the level of agreeing on ASCII character sets or Unicode character sets and so on. Today, the Web 2.0 people make a big deal about agreeing on bags of XML terms. The problem is that if you talk to 27 different companies, while you can get them all to use /employee to mean employee, they're going to mean 27 very slightly different things by what is and is not an employee. Do you consider consultants employees, seasonal employees, temporary employees, and so on? Or what it means to be a /company vehicle. Are your forklifts company vehicles? Now, if all you're doing is information retrieval, then those little tiny semantic divergences, those little tiny semantic mismatches won't matter too much. But if you really are asking questions that require arithmetically or logically combining pieces of information from 2 or 3 or 7 different sources, then those little tiny mismatches will combine to very often give you a genuinely wrong answer. So that's why those of you may have noticed the article in the New York Times that John Markoff wrote in which he sort of announced Web 3.0, which I guess means it's we'll have to start calling it that from now on. But basically, what you might call the real semantic web will basically have to go beyond that agreement on bags of XML terms. We'll have to agree on most of the meaning of most of those terms expressed in some more or less formal fashion. And we'll also have to agree on much more sophisticated and much more extensive sorts of metadata, not just the time at which something was entered on the web or the source or provenance, but also more semantic metadata attributes like who believes this to be true, when was it believed to be true, how certain is it, what's its epistemological status, and so on. So until we agree on the content and the context, we're only going to have a false peak for the semantic web. So as Eric and I have both mentioned, this has been going on a long time, our effort to build the psych inference system and knowledge base. The motive for this was pretty much that we kept hitting a brick wall. People like Bob Bowles doing robotics research back at Stanford when I was there, and in natural language understanding and speech understanding in expert systems, we kept hitting the very same brick wall, which is we'd build these systems and they'd have wonderful properties in the small. We'd have wonderful little demos, and they just wouldn't quite scale up. And they wouldn't scale up because they didn't really have common sense. And so they'd work for their little demo areas, but then whenever we tried to apply them in ways that were not quite preconceived, there'd be 1 or 2 or 3 random pieces of information that they would lack that would keep them from succeeding in this new situation. and integrate it out over all the new possible situations. What that means is that there are these millions of little tiny mattresses in the road that need to be cleared out of the way if you're really going to ever have machine intelligence. So about 1983, I and a few other people, Alan Kay and Marvin Minsky and Ed Feigenbaum, all started saying the same thing, that somebody needs to codify all this general knowledge. About that time, we actually had the means for the first time. America was scared to death of the Japanese fifth-generation computing effort. Japan had threatened to do in software and hardware what they'd already done in consumer electronics and the automotive industry, namely wrest control away from the U.S. once and for all. And so the Justice Department granted a dispensation to the antitrust laws to large American companies to come together and form a consortium, MCC, which Admiral Bobby Inman formed in Austin, Texas, which is pretty much why I live in Austin, Texas today. So he came to see me. I'd been a Stanford professor for a long time. And he said, look, if you're really serious about this mattress in the road problem, it's going to take, 1,000-person years of effort to solve. You've got how many graduate students? 6? You do the math. Do you want to spend the next 200 years here as a professor, or do you want to move to the wilds of Austin, Texas, and possibly live to see the end of this project? So it was a close decision. But in the end, I chose to move to Austin. And to make a long story short, that's pretty much what we've been working on for the last 20 years. We've just about spent our 1,000-person years of effort. For those of you just tuning in to this effort, the good news is that by having skipped the first 22 years, you sort of tuned in at the exciting part of the movie. So our motivation was, as I mentioned, that software used to be incredibly brittle. We had lots of examples, and in honor of Eric, I have some old medical expert system examples of things like, this is actually not one of your systems. This was Alain Bonnet's skin disease diagnosis system, where we tell it about my rusted out old Pontiac, and it would ask questions, like, are there spots on the body? Yes. What color? Reddish brown. More on the trunk than elsewhere? No. And it would diagnose it as having measles. Or John McCarthy once asked the Mycin program about someone who'd been dead for a week, and it, blithely diagnosed what kind of meningitis they should be treated for, and that kind of thing. So
John was complaining to me that he typed in "I'm sick" to Mycin and was very upset when it gets the error message back.
Yeah, so there's all sorts of, right, exactly, all sorts of brittlenesses like that. Or there was a Fortune article about a car loan approval system that granted a loan for someone who said they'd been born in 1980, but they'd also worked at their current job for 29 years. So they're mistakes which no human would make if they gave it even a modicum of thought, but which computers make because they happen not to know some particular piece of information. Like, for instance, it's better to run over a dog than seriously injure a child. That's the kind of piece of knowledge which many of you who've watched Stanley Kubrick and Arthur C. Clarke's 2001, A Space Odyssey, a lot of people didn't understand why HAL, the computer HAL, killed the crew on the spaceship. But it basically was exactly that kind of ignorance where Hal had been ordered never to lie to the crew, but Hal had also been told on this particular mission he had to lie to the crew and keep the details of the mission secret. And so Hal found this elegant solution, which was to kill the crew. Then he didn't have to lie to them, didn't have to not lie to them. That's because nobody ever told Hal that it's better to lie to somebody than to kill them. So basically, it's now decades later, but software is still brittle. If I go to the web and I want to find out if the Eiffel Tower is taller than the Space Needle, I can't just type in the question. If I want to find out what PG-rated movies I could take my kid to that start in about an hour, not too far from here, it's annoying that I can't just ask questions like this. And if you go to Google and type that in, basically you get pages from which you could calculate the answer, pages which you have to ignore, because it turns out some of them deal with replicas of these items in Las Vegas, which have heights that are obviously different than the originals and so on. And yes, of course, if you do arithmetic, then you can find the height of the Eiffel Tower. You can find the height of the Space Needle. You can do the subtraction and figure out how much taller one is than the other. But why should we, as human beings, have to go to these different sites and do this arithmetic ourselves? So there are lots of missed opportunities by not understanding what the pages say, not understanding what the user is really saying, not being able to combine logically and arithmetically pieces of information from 2 or 3 of these pages, even in something as simple as the heights of the 2 buildings. And there's a real danger in giving power to computers, which we're doing more and more and more every day, in areas where basically we wouldn't trust human idiot savants, like, for instance, treating our children medically. Or there's always this talk, every 10 years or so, there's this craze about how home robots are just around the corner. They're going to mind the baby. They're going to cook meals. They're going to mow the lawn and everything. And then it never really materializes because, of course, without common sense, the robots would just as blithely mow the baby because they don't know, they don't care, they don't have common sense, they don't know that one is a bad thing to do. Basically, our software today has the veneer of intelligence, but without actual intelligence behind it, which is a very dangerous situation, just like if you have human beings that you know who have the veneer of intelligence, and that's all. It's really dangerous to give them a lot of power. I could give you examples, but I'm sure you could think of your own right now. So in terms of software, the example that I've used for decades, and it's still a fine example of what I mean by the veneer of intelligence, is the ELIZA, or doctor program that Joe Weizenbaum did at MIT 40 years ago, based on Rogerian psychiatry, parroting back, reflecting back what you say to it. So you say, I'm trying to smoke, I'm trying to quit smoking, and it says, tell me more about the fact that you're trying to quit smoking, or something. So in this case, you're saying to the system, my dog's mother died recently, and the system says back, tell me more about your mother, which sounds like a really deep psychiatric insight, but it's mostly unless you don't know how programs work. In this case, it simply doesn't know the word dog, so it sort of heard blah, 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 mother, and it said, tell me more about your mother. It's a lot like the Gary Larson Far Side cartoon of what you say to the dog and what the dog actually hears. And for those of you that are dog people, I will show you the rarely seen cat version of this cartoon of what you say to the cat and what the cat hears. But anyway, so yeah, that was 40 years ago, but surely things are a lot better now. It's 40 years later. And yet, if you look at the Turing test competitions, the Loebner competitions, the winners, by and large, are these little chatbots like Alice, where you say things like this, and it gives you this horrible, in this case, garbled, Eliza-like parroting back of what you said to it. Or where's Sue's nose when Sue's in her house? And it says, where it belongs. Now, this is actually not a bad answer, but it ruins it by going on and saying, try searching the World Wide Web. So obviously, it's just matching questions like, where is X or something like that. If you go to Ask Jeeves, again, you basically get the same results you'd expect from a site like Lycos or Google, namely some Boolean combination of keywords, in this case just a bag of keywords, and that's about it. If you go to Encarta, it's sort of strange. You get 2 hits, one on the history of automobiles, and one, I guess because of some kind of capitalization misunderstanding, on the Central African Republic. But anyway, you don't actually get the answer to your question because it doesn't really understand what the question is. And obviously, if you go to Google, you don't get a good result either because it's just taking those as a bag of words to search on. So the basic idea here is that we want the computer to understand, not just appear to remember information. And understanding means having the ability to reason and conclude the same sorts of deductive conclusions that you or I would from the information that it's been told that it could combine. So, all right, so why don't we just tell it the millions of things we need to tell it about the world we live in? And in fact, if you're not careful, you sort of fall into the obvious trap of, let's tell it that in English. And that ought to be relatively fast. Not very fast, because most of this is stuff that we learn by the time we're about 2 or 3 years old, and generally isn't written down anywhere. In fact, if you go to the web, often you find the negation of the things that people know about the world. Like if you look for hits on water flowing uphill and water flowing downhill, there are a lot more occurrences of water flowing uphill on the web because it's a metaphorical, dramatic statement. Everybody knows that water flows downhill. You don't have to say that to people, and so on. So there's a lot of times that you find wrong information out there. But even so, stating it in English is not really going to do the trick, basically, because while here we appear to have told the system about microwave ovens and dishwashers, in reality, even though you know what those words mean, if this is all we've told the system, it has no idea what these things are. It has no idea how microwaves are different from dishwashers. You know, we might have used made-up words like this, and if I had used this on the slide, you wouldn't have known which was which either. Yeah, we go on and we have to state additional information, like the first one requires electricity and the second requires electricity and water. But again, we have to sort of axiomatize electricity and water and tell things like water comes to your house in pipes in liquid form. And even relationships like requires have to be axiomatized. So if an item, a device requires some resource and it doesn't have it, then it's going to stop functioning, that kind of axiom and so on. So the idea is that eventually, if you keep this up for year after year, decade after decade, millions of times, eventually there's just one interpretation that satisfies all those axioms. And it's the one where buzzqua is water and get the whatever is microwave oven and so on. And if you keep on doing this, you can begin to trust the conclusions that the system puts out as being likely to be true in the real world. So I'll give you some examples now and at the very end of how this might actually affect your life, and both in terms of the applications you run and the applications you guys develop as well. But in terms of just information retrieval, finding information out there, here's a simple example of a system that we did several years ago for finding captioned images. Captioned images are good because the captions, the actual documents, are very short. They may be only 5 or 10 words long. And so if the caption is short, you can't count on the document to contain exactly the same words that your query is going to contain. So for example, in this case, you know that there's a match, and the psych system knows there's a match because of a few pieces of common sense, like parents love their children, and if somebody you love accomplishes something, it makes you happy, and if you're happy, you smile, and taking your first step is an accomplishment. So if you know those 4 things, then finding this match is trivial. If you don't know those 4 things, finding this match is basically impossible. And that's really the trick. That's really the secret of what we're doing, is sort of using general knowledge to convert impossible problems into trivial ones. Here's another example where it's finding a match between this caption and the query for pictures of strong and adventurous people, because it knows that if you're doing rock climbing, you must be at least moderately strong and moderately adventurous. So we're not talking about beating Kasparov at chess. We're not talking about 37 deep reasoning. This is like 1 or 2-step reasoning. If you have this knowledge, finding this match is easy. If you don't have the piece of knowledge, it's pretty much impossible. It's not like Google could add 15,000 servers tomorrow and find this match when they didn't find it today. If they don't have the piece of knowledge, they're never going to find it. There's nothing special about captioned images. This is from a more recent intelligence agency application we're doing, where the documents are having to do with terrorist incidents. And in this case, the question was about government buildings damaged in terrorist events in Beirut. And you have to know things like embassies are government buildings, and if there was a pipe bombing, then presumably there was some damage that was done, and so on. So again, domain-dependent, or in some cases very domain-dependent, knowledge might actually be required. There's also the same kind of knowledge required to do consistency checking, like noticing in this employee spreadsheet, HR spreadsheet, that this person seems to have been hired before they were born, and it looks like they listed themselves as their own emergency contact, and so on. So these things don't violate so much the schema of the database or the schema of the spreadsheet as they violate common sense. And you could say, well, why wasn't it the obligation of whoever put this together to have thought of all of those different constraints and written them down? Well, in reality, there aren't 8 columns, there are 80,000. And they're not spread out in one table. They're spread out in thousands of tables, in hundreds of databases out there on the web. And it's only because you happen to know what these column names mean, or can figure out what the column names mean, that you realize that some of these constraints should hold. So the basic idea then is that by having lots of knowledge in machine manipulable form, our programs could actually go beyond just the veneer of intelligence. I could give you lots of examples, but I'm going to pick a few examples just to illustrate this from natural language understanding, from disambiguating polysemous words and pronoun references and things like that. A lot of these examples are 20, 30, 40 years old. So this is not like new examples. These are things that people have known are problems for a long time. And it's very hard to see how to fix this if you don't actually have pieces of knowledge like how big things are to decide what kind of pen you're actually talking about in each case. Or an old Terry Winograd example, the police watched the demonstrators because they feared violence versus because they advocated violence. One of the theys is going to be the police, and one of the theys is going to be the demonstrators, and so on. Or if I say Mary and Sue are sisters, you assume I mean they're each other's sisters because so many people have siblings that if I really meant they each just happened to have a sibling, that would be a misleading thing for me to say. On the other hand, if instead I had said Mary and Sue are mothers, it would never cross your mind for a second that they were each other's mothers. And that has nothing to do with like linguistic theory exactly. It's sort of your knowledge of biological reproduction and what's possible, and back to this piece of knowledge about causes have to precede effects and so on. Every American has a mother. It's not the same mother, but it is the same president. John saw his brother skiing on TV. The fool didn't have a coat on. Presumably the fool is the person skiing. But if I had said the fool didn't recognize him, the fool would presumably have been John, the person watching television. So again, it's your knowledge of television and skiing and weather and stuff like that that enables you to answer these kinds of, do these kinds of disambiguations. So basically, we're talking about having a large corpus of knowledge and representing it in some formal fashion. We can refer to the words as the ontology if we want to be fancy. We can talk about this as being a formal ontology, which means that we actually have a whole bunch of these axioms or rules stated in a formal logical language. But the reason for using an ontology is the same reason for using any kind of hierarchy. For one thing, it helps you focus where information applies. So it applies to a node and its specializations. It helps you position new information. So if you know that water vehicles slow down in bad weather, you look around at the ontology and you say, well, that really applies more to surface water vehicles and really applies to surface vehicles in general. So even though you didn't have trucks in mind when you wrote the rule, that rule now applies to that truck, and you would predict that that truck would slow down in bad weather. And I think most of you in this audience are sophisticated enough to know what I mean when I say represented in logic, namely have some formal language from which we could conclude the same sorts of deductions that you or I would conclude. For instance, from Socrates being a man and men being mortal, conclude things like Socrates is mortal. Or one of my favorite examples that most of the people at PsyCourt don't like as much as I do, but is can. Just to illustrate that this has nothing to do with natural language, because the internal representation, I'll switch to an English paraphrased version, basically has nothing to do with the English word can or can or can or whatever, because by the time the system reasons with them, those ambiguities have been taken away, and there's a unique way of representing can dancing and so on. By the way, the argument here is that cans can't do can dancing because they're inanimate objects, and can dancing pretty much requires having a brain as well as a body and so on. I could give some examples from some of our earlier systems in terms of the reasoning that they did that involve combining pieces of information from lots of different sources. So I'll give you one example. This is a project we did for DARPA several years ago. Basically, in this case, intelligence analysts were asking questions like, if because of some blockade, only Saudi oil is allowed to transit the Bab el-Mandeb Strait, could OPEC make up the supply loss to the world by snapping its fingers and increasing its production without actually having to build new production capacity? And in this case, the programs mostly said, and the experts mostly said, I don't know, because the countries keep secret the amount of oil they ship through the strait. But Psych was able to give the answer yes, and when asked why, it basically combined information from about half a dozen different places. So from one place it found out the total amount of oil flowing through the strait, so the amount of Saudi oil and non-Saudi oil has to be somewhere in the range of 0 to 3.4 million barrels a day. From another place it found out what OPEC could have produced if it had wanted to during that year, and from another place it found out what OPEC was actually producing. So if you subtract those last two numbers, you find out how much OPEC could have increased its production by if it had wanted to. So it doesn't really matter what this number over here is. It's smaller than this number over here, so the answer is yes. And there were a lot of cases like that where the expert looked at the answer and the justification and said, oh, yes, it's obvious that's the right answer. There are also a lot of cases where it got the answer wrong, but we don't have time to go through any of those cases. But it's not, it's like the dancing bear. It's not so much that it's doing a great job, it's that it ever works that's sort of impressive here. So nowadays we have an application called the Analyst Knowledge Base, and we're having a little bit of audiovisual trouble in terms of projecting it, but I have it running up here, and so afterwards, if some of you are interested, we could try to ask it some questions. But a lot of our funding these days comes from the Department of Defense and from the Office of the DNI and from intelligence agencies. So a lot of psych's expertise now in terms of outside of common sense, what domains is it been populated with? A lot of that expertise is in the areas of terrorism and counterterrorism detailed knowledge. So a lot of the questions, the hard questions that it can answer these days have to do with possible terrorist attacks and thwarting those. But basically, there are things like if you ask who had a motive for assassinating Rafiq Hariri, the former Lebanese prime minister, basically, after a minute or so, you can get the question asked of the system, and it comes back with several surprising answers, like Israel and the U.S., but if you look at the source icons, you can basically see that it's some Al Jazeera editorial which is actually accusing the U.S. and Israel of colluding to assassinate Hariri. Now, on the one hand, you don't want to believe that without listing the source icons. On the other hand, you don't want to just ignore that, since there are millions of people in the world who do believe that to be true, which is why it's important to contextualize these by explicitly having the sources and possibly ordering this by source and so on. There's also information that Western analysts would agree on, which is that Syria was probably at fault here. And if you ask why, it says that it's speculative because there's a clause in the justification that it's not 100% sure of. And so you could say, yes, this is true, or no, it's not true, or I don't know whether it's true or not. If you say, I don't know whether it's true or not, then it'll generate a web query and go out and help you find the information from which you could actually answer the question. So one of the applications that we have of psych nowadays is the kind of semantic searching, where you put in a query, and it finds hits more sort of better in a little way than just syntactically pulling together bags of keywords. In this case, you've asked it about the Faithful Resistance, which it recognizes to be a terrorist organization. And so it's found some hits that mention Mustafa Durrani, even if they don't mention the actual organization Faithful Resistance, because he's best known as the head of Faithful Resistance. And conversely, it's eliminated an awful lot of web pages if you just do a plain old Lucene search. It's eliminated all these spurious web pages that just happen to mention the words faithful resistance, which are not actually talking about the terrorist group at all. So you end up with less false positives, less false negatives by doing this kind of simple ontologically aligned searching. So you could think of everything we just talked about in terms of question answering and so on as sort of fitting in a band between the typing in a question and the normal sort of hits you would get from some search engine. So that's sort of the way that we envision this being used. We also do semantic knowledge source integration of databases and websites and other structured sources using psych as a kind of interlingua. If you're not careful, you end up with a kind of n-squared problem in integrating information from multiple sources. Here we have different databases with different information about individuals, and if you ask how different in age were Qusay and Uday Hussein, neither of these databases can answer that question, but you as a human being, using knowledge of things like things age 1 year per year and so on, and psych, which also knows that, can answer the question by doing some arithmetic, and basically you come up with the fact that they were 2 years apart. You can also do something cool, which is you can put in 1966 there with the justification of this number 30 here, and you can put a 32 here with the justification of this number 1964 here. And if you want, you can even then throw psych away and basically be left simply with enriched databases at the end, enriched knowledge sources. So that's sort of a cool thing, and we're doing that for various applications. One recent one involved sort of possible sites for terrorist attacks by pulling together knowledge of weather and susceptibility to various sorts of attacks, severity based on accessibility of hospital beds in the area, and so on. So here's a case where, among other things, the system had to figure out which cities in the U.S. had population over 1 million. These are the same 4 rows just spread out because I didn't have room to put them all here. So this is basically saying Dallas has 1.02 million people. And in order to get this to work, we have to write rules in the system, assertions that explain the meaning of the elements of that schema. So there's, for instance, this assertion which says that the population field of that table of that database contains the number of inhabitants of, well, the number of inhabitants of what? The number of inhabitants of the referent of the row of that database. And very often, this turned out to be a concept it took us a while to actually work out as being important and actually very commonly useful, which is the very existence of a row in that table means there is some geopolitical entity somewhere. And so it's referring to a geopolitical entity. So it's referring to something. And so it's that thing that is represented by the existence of the row, which has the population 1.02 million people and so on. Other assertions having to do with protocols for accessing it. Other assertions which tell you that this is a really good table to use. Other assertions which tell you statistically how many things you would get if you were to ask for them. Like, for instance, how many named objects are there typically in, if you're given a county and a state, how many named objects do you have the longitude and latitude for? The answer here in this table is about 530. Or if you just ask how many different entries are there in the state column, well, you might think there should be 50, but in fact there are 60, probably because there are things like equivalents of don't know and District of Columbia and stuff like that. By the way, in case you wondered, the lucky winner was Phoenix, basically because they had a lot of people and they were warm enough for the spores to germinate, and they had a lot of suitable zoonotic hosts, and they didn't have a lot of hospital beds. And if you ask things like, why wasn't Philadelphia the lucky winner, it would say, well, it was too cold the day you asked, and so on. So overall, we have our axioms divided up into contexts by granularity, by time, by space, by culture, and so on. And while there is a single reasoning mechanism which would work, namely theorem proving, in reality, in pragmatic terms, that's too slow. If you're ever doing theorem proving, it's sort of like calling on the kid in the back of the room who always has his hand up or something. You don't really want to do that unless you have to, because you just know you're going to be sorry if you do. And it's sort of the same thing here, where we now have over 1,000 specialized reasoning mechanisms, and we try to call on the most efficient one that raises its hand, and only if we have to sort of grit our teeth and call on general theorem proving. Almost all the knowledge is non-monotonic. Almost nothing that you know about the world is absolutely true. Almost all of it is only true in some context. Like, remember what we said about Rafiq Hariri, or even something like each person has a mother who's also a person. It doesn't matter whether you believe in evolution or creationism. You believe there have only been a finite number of people. So it can't be the case that each person had a mother who was also a person. So almost everything you know outside of mathematics is really just approximately or usually true, or true by default. So by and large, the system reasons by argumentation, by gathering up the pro and con arguments and deciding which ones to believe, which ones outweigh the others. although I've mentioned a couple times the number of concepts and the number of assertions or rules in our system, you should take that with a big grain of salt. We go out of our way to make those numbers as small as possible, not as large as possible. If you ask, how many questions, sort of like, is Cher a moose, could the system answer? The answer is going to be like 100 trillion. Or how many type questions, like, are seagulls also mooses ever? Basically, they're on the order of hundreds of millions of questions like that it can answer. But the way it answers them is by having simple Linnaean taxonomy and a statement about disjointness, namely 2 taxons which aren't related by specialization are going to be disjoint. And now with 10,001 rules instead of 100 million or 100 trillion, you can answer pretty much all those questions. So we're constantly looking for ways to keep the numbers of axioms as small as possible, not as large as possible. I don't have time to go through the content of the knowledge base, but it pretty much spans all the things you might imagine, like relations between things existing in time, or the kind of knowledge you'd need in order to conclude things like, in this case, Condoleezza Rice and Ariel Sharon must have been in Jerusalem for at least 3 days during February of 2005. Or different kinds of parts, like if you ask if the Sonora Desert is part of the sum of California, Arizona, and Mexico, there's an important sense in which the answer is yes, and the system should really give you a yes answer to that question. In terms of like representing physical containment, the notion of physically in, X being in Y. In 1984, we just had one predicate in, but slowly over time, that expanded because the way that you're in this room is different from the way the air molecules are in the room, which is different from the way that this dollar bill in my pocket is in the room, and so on, in terms of visibility, or what would happen if it were turned upside down, and so on. So eventually, over the years, we've had to add something like 75 different meanings of in to the system, and if you don't make those distinctions, then they're going to be questions that you just get wrong that you otherwise would get right if you make all those distinctions. 11,000 kinds of events, 400 roles that an actor can play in an event, information about emotions and what causes different emotions and so on. Lots of propositional attitudes, most of which are what you would call modals, believing, intending, desiring, hoping, expecting. And you need to be able to represent nested modals, like following the recent election, Israel's afraid that Egypt is going to want the U.S. to try to convince Iran, ... that sort of thing. If you can't represent statements like that, then again, they're going to be elements of everyday news, elements of human common sense that you simply are lacking. And so it's dangerous to have under-expressive languages. Lots of information about devices and so on. This is a diagram we've shown for about 20 years. The good news is that we're sort of at the end point of this. We talked about machine learning, where you learn more based on what you know already. But unfortunately, if you're way over here at the x-axis, you don't know that much, you can't learn that much. And a lot of our machine learning programs 20 years ago, 25 years ago, were stuck back near that origin. So it's very painful to use machine learning if you have to start out with essentially nothing, priming the knowledge pump, as it were. You could say, well, contrast that with learning by being told. Well, all those examples we saw, like the pen is in the box, make it very hard for the system to understand by being told, understand by reading things out on the web, unless it already has common sense. And yes, eventually you have to fall back on machine learning, but when you're way over at the left edge of the curve, both of these are sort of inferior to the sort of ugly duckling tactic of just manually writing down all the damn rules one after another. So this was like the really sad realization that we had in 1983. It's sad because there's not really a lot of science here. There's at most engineering to get that crossover point achieved. And as I said, it was almost 1,000 person years of effort to get there. We got there in 2004. So the last couple of years, we've mostly been moving from this mode of manually adding knowledge to the system to automatically adding knowledge through machine learning, through natural language understanding. It's a very exciting time for us. An example of what I mean by this is going out to the web and fishing. So for every organization, there are 100 things you want to know about the organization. When was it founded? Who are its leaders? Where's its headquarters? How does it get its money? And so on. And For each one of those, we can do natural language generation, generate alternate ways of saying those things in English, go out to the web and fish for those, and by gosh, you often find exactly what you're looking for somewhere on the web, because the web is really, really big. And there's a good chance that if you have a few alternate ways of saying it, someone would have said it that way somewhere. So you go out and you fish and you get information, and then you can add that to the knowledge base if you're courageous enough. Here's a case where we wanted to know the height of the Eiffel Tower. We went out and found it. And it turns out some of them that you find are wrong, but you can use common sense to decide in cases where there's a genuine disagreement, which is probably the right answer. By the way, in case you wonder where it got the 36 feet from, it's the very first hit returned by Google because it didn't quite parse the sentence correctly. But anyway, in a case like marital status, there aren't that many marital statuses. So for each one of them, you can do what we just said. And then you find out what the person's marital status was, and even better, what their marital status was at different points in time, and so on. Now, I said if you're courageous, because the problem is that, as we saw over and over again, a lot of the material out on the web is just wrong, just plain old wrong. It's fictional, it's a lie, it's metaphorical, it's for dramatic effect, it's someone's idiosyncratic belief, and so on. So basically, what we had to do was, by the way, this is like an example of, what parts of the body are hats worn on. Well, an awful lot of the hits out on the web don't actually say hat on his head, because everybody knows that's where hats are worn, so they only say things that are cute or dramatic or whatever. So basically what we had to do was to find a way to vet or filter the 50% of the good stuff we were getting from the 50% of the bad stuff we were getting. So what we came up with was the idea of having a game. In some ways, this is the analog of what Louis van Aan has been doing at CMU with captioning images. In our case, what we do is we have people play this game, and they're asked, I think we can actually do this live. So here, the danger is that some of these questions may be a little bit weird, but that's okay. So now 10 people are somewhere in the world are simultaneously being asked this question. And so aisles generally do live longer than diaries, but maybe not that many people agree. And to an order of magnitude, how big is a motor scooter? I'm guessing it's about person-sized. That's probably true. And that's probably true, and so on. I'll stop this in a second, but you can see it's very addictive. And after you've answered this for a while, you get scores, and you get points, and eventually you get to compete with other people, and so on. So from the people point of view who are playing this, they're just playing a game. From our point of view, they're giving us free labor to disambiguate and vet information out there. So by now we've gotten something like 500,000 people playing this. And soon we'll have gotten to the point where more than half of the content of Psych will have been put in through the sort of fishing and vetting process, rather than the kind of cloistered philosophers, logicians, manually putting information in that we did for the first 20 years of the project. That's sort of an exciting statistic. I can skip through that. Okay, so we talked about this already. This is just basically making the point that if you talk to folks who work on like RDF or OWL or DAML or something like that, basically the problem is that not that they're making an error, just that they're believing that you can get by with just agreement on 10 or 20 or 30 different relations or types of attributes and so on. It's sort of like saying if you were translating Hamlet into any subset of English you wanted, where I'd let you use any 50 words you want. You could use all the proper nouns in Hamlet, plus 50 words that were not proper nouns. and you have to pick the 50 words and then translate the entire play using those 50 words. It's going to be a nightmare, and it's pretty much the same nightmare for exactly the same reason, namely that if you're not careful, you haven't made enough distinctions, and you just start getting a lot of questions wrong if you don't make enough distinctions. As I've sort of hinted, there's no actual correct ontology. It's very contextualized. So, if your spouse asks you to bring home some of those red flowers they like, and they mean poinsettias or something, and you show up without them, and they say, where are they? And you say, oh, it turns out poinsettias aren't actually flowers. Okay, that's like not in your best interest to do that. There's sort of like common sense ontology in which apes are monkeys and poinsettias are red flowers and so on. There are lots of different representations that are semantically equivalent to each other, and it's not like there's any one of these which is better than the other. It's not like there's any one of these which is correct. So you really need to make all these different distinctions and interrelate them by saying this is what the average American believes about, this is what the average 7-year-old believes about the world, this is what most adults in 1940 believed to be true about the world, and so on. So you need that kind of contextualization. And by now, every assertion in psych is contextualized to the context in which we believe it to be true. So if you say, is Dracula a vampire, most people would say yes. But if you'd also asked them, are there any vampires, they would have said no. It's that kind of contradiction if you're not careful. Or like if it's raining, should you carry an umbrella? As people in Seattle know, the answer is like usually. Well, actually, in Seattle, probably people ignore the rain. But in most parts of the country, the answer is yes. But there are all sorts of exceptions, like if you're talking about non-humans or babies or people living before the invention of umbrellas or things like that. So basically, each assertion is contextualized using a kind of ist format like this. We have by now about a dozen different major ways in which one context can differ with another. I think I'll sort of skip some of this, but basically it's not obvious how you automatically conclude if P is true in one context and P implies Q is true in another context. How do you conclude exactly in what context Q should be asserted? Turns out to be a very complicated problem, and it's one that we're spending a lot of our theoretical time worrying about. In terms of the caveat emptor category of buyer beware, I'll sort of list here the 5 ways in which most people who claim they have semantic technologies are actually cutting corners. And to be fair, I'll say that we do some of all these things as well, but we do less than most people. So one of the problems is giving in to the temptation of being ignorance-based. By having fewer assertions, more of them are going to be relevant. A higher fraction are going to be relevant. In the extreme, if you only have 7 relevant pieces of information, and that's all you know, it's really easy to decide which 7 pieces of information to combine to get your answer. Static knowledge bases. If you're not careful, you end up with a system which is highly tuned for a static knowledge base, whereas in a lot of problems, like Eric was telling us yesterday about the traffic flow stuff that you're doing, the world is changing every few seconds or even every fraction of a second, and you can't have the luxury of taking a knowledge base and fixing it for a month and doing some kind of optimization on it. A third sort of pitfall of most semantic technologies is picking a representation language which is unexpressive, which is too simple. And you get efficiency that way, but you throw out part of the baby with the bathwater. If what you're doing is deciding what courses should go on in what classrooms at a university, simple SAT solvers might suffice. But if you're trying to do reasoning about courses of action in Iraq or something, it could be very dangerous to pick too unexpressive a representation language. The fourth one is somehow assuming that everything's going to globally fit together consistently. As we saw, there's the need to contextualize because things are true in one context and they're false in another. So the way our system works is basically to reason within a context and slowly do a kind of spreading activation farther and farther afield as it needs to. And that works because the knowledge base is locally consistent in much the same way that you live your life as though the Earth's surface were flat. Even though in your mind you know that it's a sphere, it doesn't matter because locally it is flat. And you can get by most of the time without worrying about the fact that it's spherical. In much the same way, our knowledge base, even though it's inconsistent, is locally consistent. We can get by acting that way. And then finally, the dangerous assumption that whatever you've been told and you've concluded, you can count on forever. Almost nothing has that property. There's no telling what you might find out tomorrow that would cause you to invalidate something that you were told today, or some complicated consequence of something that you believe to be true today. So you really have to have kind of truth maintenance on all the time. The way that people use the system is generally to extend the ontology to add more terms, to extend the knowledge base to add new rules or assertions, and in rare cases, modify the heuristic level mechanisms, the reasoning modules, in rare cases, modify the interfaces, and so on. We've released the entire psych ontology for free for anybody to use, even for commercial purposes. You're more than welcome to make use of that. We also have released for research purposes the rest of psych, all the millions of rules that talk about those terms and so on. And we have a lot of people that are using research psych by now. I made a list in 1984 of what I thought the winning applications for psych would be 20, 25 years in the future. Almost all of those I still agree with. And in terms of things you guys are doing here, some of the relevant ones are things like machine translation. Because sometimes 90% accuracy, or whatever it is you can get these days, just isn't quite enough. Like if you have legal contracts where mistranslating a single pronoun reference is going to cause the meaning to shift of the contract, or whatever. Or doing translations like these. Like if you want to translate into Japanese a sentence like, Mary filled the tea kettle with water. After it whistled, she poured the water into the cup. In Japanese, you need to use different words for cold water initially and hot water eventually. But how do you know the water starts out cold and ends up hot? Well, it's because of your knowledge of tea kettles and so on. Or speech understanding. Sometimes 95% or whatever you can get these days isn't just going to be enough. It might be in some narrow niche area, like bedside intake interviews with hospital patients or something. But in general, it's not quite enough across domains. And when I was helping to start Microsoft Research about 15 years ago, we actually started some speech understanding projects. And there was a lot of hope that we could get by without this kind of common sense knowledge. And I'm still waiting for the general domain-independent speech to emerge. Meanwhile, we've gotten the common sense stuff put in enough that we might be able to help with this problem. The two examples there, one was Alan Kay asked me how we were doing, and I said, good, I've hired 10 people last month. And he said, oh, that's terrible. And it took me a while to realize that he thought I said I fired, whereas in fact I said I've hired. If I had prefaced that with, we just got a big new contract, ... then he would have understood it the right way. Or back when Bell Telephone was Bell Telephone, they did some study on signal-to-noise ratios on scratchy phone lines. And they kept getting results that were above the theoretical maximum because people's brains are so good that they could actually correctly figure out what other people on the other end of the line were saying, even when there wasn't really even theoretically enough signal there to figure it out. In terms of things like Microsoft Word, spell checking, I'm sure as you've noticed, doesn't seem to be very context sensitive. Grammar checking and style checking sometimes hit, sometimes miss. The paperclip assistant has gotten better and better, but still sort of annoying in that it doesn't quite understand a lot of times what I'm asking. Then there's also possibilities like content checking. Like I say in this Microsoft Word document below, I'm going to talk about X, Y, and Z, and I never talk about Y. It would be nice to highlight the Y in some color until I either change that sentence or actually talk about topic Y somewhere in the article. In terms of things like spreadsheets or simple relational databases, there's all kinds of possibility for automatically understanding or semi-automatically understanding some of the meaning of the columns or the relations, and then using that knowledge, like we saw in the case of the hiring date and birth date and so on, to basically detect probably incorrect usage of a column or unstated relationships that constrain column values, or noticing even that we could guess at the value of a certain cell entry would be pretty cool. Summarization and prioritization of text. things like spam filtering. If I go on vacation, should this message that comes to me just wait for my return? Should it follow me on vacation? Should it go to the person who's now doing my job at that company while I'm on vacation, and so on? Noticing contradictions, like I just accepted 2 different appointments that I'm not going to be able to spatiotemporally get from this one to that one, even if they are 1 hour apart. There's sort of more than a 1 hour commute between them, that kind of thing. And all that goes double for places where you don't have a lot of screen real estate, like if you're trying to quickly scan your voicemail messages from a phone. Shopping and matching up buyers and sellers, matching up people who have jobs to offer and who want jobs, matching up people who want to donate things, like if it's really a children's hospital, they may not really want hockey sticks, even if they do want games and toys and other things that hockey sticks might be in the same category as, and so on. And so here's a case where we gave advice about tours, knowing things like this person was a nurse. Then a free day in Geneva was a plus because that's where the Red Cross Museum is. And knowing that someone had trouble walking, we sort of warned them about some tour that involved a lot of walking over uneven ground and so on. Games, especially massive multiplayer online role-playing games. There's all sorts of problems with NPC realism because, in fact, the NPCs don't have common sense. So if you ask them pretty much anything that wasn't preconceived, there's a good chance they're going to give you a bad answer, and there's a good chance their behavior is going to be pretty heavily scripted. And if you say, well, why do various MMORPGs come to an end? It's usually because the players come to the end of the content, and they get bored and they move on to some other new MMORPG that's come into being. But if, in fact, you had the same kind of common sense we've been talking about, you could begin to generate new content automatically, which is a really exciting thing. Anyway, to summarize all this, I want to bring this to a close and take a few questions. We talked about the need to pull information arithmetically and logically from multiple sources. We talked about breaking the software brittleness bottleneck by collecting large amounts of information, ontologizing it and axiomatizing it, using an expressive language, contextualizing it because things are true in one context and false in another, spending 20 years in the wilderness, priming the pump to the point where the system itself can act as its own inductive bias, can help with its own education by using what it knows about the world in order to sanity check and help human beings to fish for and vet information out there in the world and to help carry on conversations to gather new information. So let me stop at this point, take a few questions, and hope that you guys had fun in this talk. Thank you. Thanks. Yes?
So you gave an example of ways that it could improve search. Has it been applied to improve kind of general search for relevance by the usual measures?
So the question was, has it actually been applied to improving general search? We did a project for Hotbot, and it got hooked in and actually went live for a month or so. Just about the time that happened, Hotbot got bought by Lycos, and the process sort of started from scratch. Then after about a year, went live on Lycos. And about a month after that, Lycos got bought by Terra, which was a Spanish company. Terra decided that, what's all this about technology? We don't need technology. Lycos' success has nothing to do with technology. Let's get rid of all the researchers. Let's get rid of all the external R&D contracts and so on. I must say that I'm pleased. Well, I feel vindicated in the path that Lycos took after making that decision. But basically, just at the stage where it seemed to get used, it sort of got something kept it from getting deployed in a big way. So we've been talking with search engine companies about possibly doing something with this, but nothing much has happened in the last few years with that.
We have a late-breaking question from high-tech technology here, my cell phone, from our Silicon Valley lab.
Okay.
And it is, can Cyc build an ontology automatically from drifting through the web through a syntactic engine?
So that's a good question. And I would say that the answer is around the fringes, yes. And by that, what I mean is that to the extent that you're talking about extending and modifying and making a little bit more precise, what it already knows, then the answer is yes. If you're talking about a whole new domain where in some sense all the terms are strange to it and so on, then it would generally not be able to do that. If you think of it as a step-by-step extension of what it knows already, then yes. But in terms of just trying to make sense out of a massive text about some domain that it has no idea what it's seeing or how it relates to everything it knows already, then I would say no. It's just not going to be very good at that.
On the psych game,
Yes, yes, there are a lot. We haven't noticed bots playing it, but we have noticed bad behavior by humans. So we had to go to a scheme where we intentionally negated half of the things that we asked people, so that you couldn't just answer yes all the time and match a large number of other people and so on. We have noted that some people are much more reliable than others. And so even though we continue to let everybody play, we weight the results more heavily by some players than other players based on their track record of how often they've been right. And eventually we want to learn enough statistically that we can decide that this particular person is very good at these kinds of questions or this domain of questions and not so good at these others. But we haven't hooked that in yet, but I'd like to. Yes?
How long do people tend to play the game?
Enormous variance. A lot of people play for 10 to 30 minutes and they never play again. There's some people who've played so much that I feel guilty as contributing to some sort of whatever problem they have. We've been feeding it or something like that. So some people have actually put in hundreds of thousands of answers, which is I find frightening. Yes.
Maybe I missed it, but what is the methodology by which you're picking the challenges to get human feedback on?
Oh, we read through the web, and that's the wrong way to put it. We basically have a large number of concepts which are partially fleshed out. Many of them are proper nouns now, like organizations and individual human beings and named events and so on. Some of them are more generic things like a new kind of disease comes on the market or a new drug comes on the market or something like that. So now what you do is for the type of thing, you look up the 100 things you'd like to know about that type of thing. That type, if it's a person or an organization, a type of drug, whatever it happens to be. Now for each one of those attributes, we do natural language generation, which is vastly easier than natural language understanding. So we do natural language generation using the lexicon we have and the grammar we have and so on to produce sort of fill-in-the-blank English strings that would be stating the piece of information if we could find this out on the web. And then we call on the appropriate search engine, which for obscure reasons generally turns out to be Alta Vista, just because of the what they allow us to do compared to what Google allows us to do, and so it doesn't really matter. But anyway, so we call on the appropriate search engine, and we get the matching strings back, and to the extent that there is general agreement, then we have a candidate assertion for testing, but we don't just believe it. It becomes something which now feeds the pipeline of this web game, so that if 10 people are now asked questions whose answers sort of trivially depend on this being true, and by which we're going to be restating it in many different ways, so it's not like the sentence that happened to be out there is just handed to the human beings. If we rephrase it based on the predicate calculus that we have, we generate natural language from it, usually very, very unlike whatever it was that came in from the web. Now, if like 9 out of 10 people say yes to this or whatever it happens to be, then we'll believe it and add it to the knowledge base. And it occurs to me that I'm throwing around these vague statistics like 9 out of 10 and so on to like the one person in the audience I should like think twice about doing it to. But I'll move slowly, I'll edge slowly away from you and take another question.
I do think it's a qualitative statement, not as a quantitative statement, that coming up with the correct or a well-founded algorithm for actually choosing questions to ask about for human mediation on would be very interesting task.
So in the case of a lot of these, what we have in the domain-dependent case, we've asked experts. Like in the case for intelligence analysis, we've asked intelligence analysts if you're finding out about a new terrorist event, what are the 50 or 100 things you most want to know about it? Or if it's a new terrorist group you've never heard of before, what are the 100 things you most want to know about it, and so on. So that basically defines our space. And for a lot of the more well-known everyday kinds of things like piece of furniture or type of communications device and so on, we ourselves are enough of the domain experts to make up our list of 50 or 100 things we want to know about that. Oh, and there's a kind of belief in incremental correction, namely, if we're wrong, then eventually we'll find that we have to keep manually adding something that we should have been getting automatically, and that'll get added to the list of things that we try and fish for automatically. Yeah.
So I guess I always have a question about your use of the term common sense in this context, because especially when you describe the phishing, it seems what you're going to be fishing for are facts rather than common sense.
Oh, absolutely.
I'd like to make a distinction between dictionary knowledge, which is about the lexicon itself, and then there's factual knowledge, and then there's common sense knowledge. And of the fishing you do, kind of what is the type of knowledge that you are actually acquiring using the fishing? And then, if you're vetting using factory only the factual knowledge, are you kind of getting more common sense knowledge, which I think you still need?
Okay, so that's an interesting point, and I'm going to have to think about, not in real time, but I'm going to have to think about why it is that we don't vet common sense knowledge. Okay, so I thought about it, despite the fact that I didn't want to in real time. It's very hard to explain to people. It's very hard to generate comprehensible to the average person sentences at the high levels of our ontology, which is really where common sense attaches to things that are related to like physical objects in general or things that exist in time in general or something. That if you look at the sentences that we would generate about that, the average person would say, what are you talking about here? And so even though the average person knows the answer, if we could only explain the question, it's very, very hard to explain the question. So by and large, there's a smaller quantity of such stuff. We've already dealt with that manually. We're already moderately happy with what we have. And it is the vast plethora of domain-dependent information, much of which is factual and is domain-dependent details and so on, that we don't have, that we will never have the manpower to do manually, that we have to do automatically, that we have to do by phishing. It's the final 99.99% or whatever of the knowledge base that has to be done this way, and it's the common sense part that we've done manually over the last 20 years that we're relatively happy with. That doesn't mean that I wouldn't also be willing to have volunteers vet and correct and extend the common sense knowledge, but I think we'd have to have a different way of doing it, a kind of almost a non-linguistic way of doing it by giving them sort of problems to solve, and that would require this piece of knowledge being true or this other piece of knowledge being true, and not try to explicitly communicate and ask them that question.
So then, when you're fishing for the specific data facts, how is it different what you're doing from know-it-all? And how, in fact, do you tie it to the concepts? Because what you're fishing is English. And you've made a point that you don't want to encode that knowledge in English.
Superficially, it doesn't look that different from know-it-all. The difference is that we've generated this sort of fill-in-the-blank template in the form that if we can find, for example, this pattern exactly with a number right here, then we could take that number and assert it to be the height in meters of a certain building or something like that. So we've basically generated this in a form where we know the exact predicate calculus representation for what the meaning of this utterance will be if we can find it with a single variable here, which would have to get filled in the text. So it's a very subtle distinction, and in terms of the way it looks to sort of someone watching it work, would be almost indistinguishable from know-it-all. Other questions? Yes.
I'm trying to understand one thing, and I'm not sure exactly how to explain what it is that I'm trying to understand. So if I think about how humans gain a lot of their knowledge, often we find ourselves suddenly dimly aware that I have some cognitive dissonance about something. Something doesn't make sense. So something that I added to my database of beliefs about to be questioned, and I don't know quite yet, and I have this kind of internal search algorithm, and then eventually I figure out, oh, this thing is actually wrong. So is when you add things to your knowledge base, is it always cumulative, or can you go not at all modality that you can add to something, or maybe a confidence level?
So I look forward to the day when the kinds of phenomena that you're talking about are what we're sort of grappling with. Right now, we're grappling with almost the uninteresting element, the uninteresting component of like something that people know. It's not really controversial. The system just doesn't happen to know it yet. And if it doesn't know it, it's going to get a whole bunch of things wrong in the future. And it's not the kind of sophisticated sort of process that you're talking about. I'd love to be working on that kind of process that involves illumination and incubation and intuition and inspiration and all the things that Poincaré talked about. All that it's like, yes, that's how I got into this. Was originally trying to get machines to do that kind of discovery, as Eric mentioned in his introduction. And it was only a kind of a 20-year detour that caused me to do this because nobody else was doing it. But I would love to get back to work in exactly that kind of automated learning.
So let me scope that question down for a moment. Oh, what if somebody made a mistake while entering basic common sense data? And as a programmer, I often find that something that made absolute sense to me turns out to be dead wrong.
Oh, sure. We believe that approximately 1% of what's in psych is wrong. And what happens is this kind of incremental detection and elimination process where at the moment, we have this conceit that it's all correct. And to the extent that that's wrong, and we know it's wrong, wrong answers will occasionally come out. So a wrong answer comes out, somebody says that's the wrong answer, or they try it out and it doesn't work, or whatever. So now that you know that's the wrong answer, you go back to the justification. You identify what the culprit was. You remove it, correct it, contextualize it. Usually it turns out it just needs to be contextualized. Like if the person who put this in wasn't actually being intentionally disruptive. They didn't properly contextualize what they said or something. So now you fixed it up, and incrementally the system's gotten a little bit better. And so slowly, incrementally, it gets more and more accurate. In a way, that's I think what happens with us, which is some fraction of what we believe to be true about the world we're just wrong about. And for some of these things, we may go through our whole lives and never realize that we're wrong about this. And it just doesn't matter.
Heaven and hell. Wrong.
Well, that would be right. So some of the mistakes are higher than others, but still, you just go through your, and so if you go through your whole life, or psych goes through its whole life, and it doesn't matter that this piece of information was wrong or something, then what does it really matter? And if it does make a difference, then presumably it will lead to bad behavior, which will get corrected in this incremental fashion. So hopefully that will either make you feel a lot better or a lot worse. I don't know which, but that's what we end up having to do because there's just too much material for it to be absolutely correct all the time. Should we take one last question? Yeah. Okay.
Were you expecting it to take 20 years to program in Common Sense, and how do you know you're done now?
No, I expected that it would take somewhere in the order of 10 years. And due to a large number of errors canceling each other out, we were only off by a factor of 2. So basically, there's much more that had to be put in than I expected. But we're also able to put it in a lot faster than I expected, but not, unfortunately, exactly as fast. So the way I know that we're reaching a kind of crossover or closure point is that the ontology is changing less and less often. The upper ontology almost never has to change anymore. We could put in the entire contents of USA Today and not have to add any general concepts at all, just add some new proper nouns to the system and so on. So there's a kind of slowing down of the ontology expansion and re-engineering process, which used to happen very often, now almost never happens, except at the very, very, very bottom levels where you have domain-dependent information. The second thing is that we have enough knowledge in the system to power this kind of automated phishing system. The NLG behind it, natural language generation behind it, and the disambiguation when you get seemingly disparate answers coming back, like the 36 feet and the 980 feet for the height of the Eiffel Tower and so on. That the knowledge of human buildings and human scale objects and so on is enough to disambiguate a lot of those things. And so it's a combination of the slowdown of some things and the speed up of some other things that cause us to believe that. And in a way, we're putting our money where our mouth is, in that the fraction of employees that we have who are doing the sort of manual knowledge entry has shrunk from about 90% to about 5% in the last few years. Almost all of the people we have employed today are linguists, are machine learning folks, not knowledge enterers, not logicians, not ontologists.
So I'd like to ask you another question. I could give your answer just now. So that's the first time I heard you say that you thought it would take 10 and it took only 20, which suggests closure. And
to get to the crossover point.
The crossover point. And how do you define that?
The crossover point is the sort of tipping point where we basically can shift most of the activity going on a day-to-day basis in most of the offices at Sitecore from manual knowledge entry to working on NLU and ML and so on.
Well, thanks very much.
Thank you.